Hi, everyone. Welcome to today's live online course, Data Structures in Java. Your instructor for today is Heinz Kaputz. Heinz is the author of the Java Specialist newsletter, where he explores interesting tips and tricks from the Java programming language. Please join his newsletter on www.javaspecialists.eu. We're very excited to have Heinz with us for today, everyone. A couple of things before we begin. We have the attendee chat feature for you all to communicate and interact with. It's located in the widget tray at the bottom of your screen. We also have the Q&A widget there, so please feel free to post your questions for Heinz right there. And then when he's around, he'll be getting to those as soon as he can. And then be sure to check out the resource list. We have an important PDF that you'll need for today's course. And before you leave today, if you can take a couple of minutes to fill out the course evaluation, that can be found all the way to the bottom right there. It's the icon that says survey. All right, with that, it looks like we're all set to begin. At this point, I'm going to pass it over to your instructor. Heinz, you're all set. You can take.
Thanks so much, Patrick, and welcome everybody back to our course. Haven't been looking forward to this course a lot because since I last taught this, I had a nice chat with one of the authors of the collections, the current maintainer, I would say, of the collections framework in Belgium. Patrick, I see your, okay. I see there's a speaker icon still on top of me. But anyway, all right, so yeah, so that was quite interesting. I went to Deques about 2 weeks ago. For the JRE, we're going to use JDK 21 today, JDK 21, because there are some new things in Java 21 that we want to look at. So make sure that you've got that. And yes, also what Patrick says, if you have any issues with your sound, the first thing to do is to refresh your screen, right? If you're the only one shouting about the sound, it's probably on your side. If you see everyone else shouting, then it's probably on my side and you don't need to shout. Then, if you see like 5 people saying sound is bad, sound is gone, then it's me, it's not you. But if you don't see anybody else shouting, there's a possibility that the problem is on your side, and simply refresh, Control Shift R for refresh, and we try again. Also, you see there's my I'm going to use the chat, the group attendee chat for communicating with you. It's the only way to communicate during the course. I'm not going to check my emails whilst the course is running. If you want to say hi, you're welcome to after the class and say, hey, Heinz, I absolutely loved your class. It was the best class I've ever been to. I'll never go to another class. I'll only come to your classes. But you're welcome to say hello. Also, if you want to join my newsletter, it's there, javaspecialist.eu/archive/subscribe. It'll take you there. And I've got a gift for you. There's the little recording of a slightly older version of this course, but it's also more complete than what we've got time for today. And the recording comes with a quiz. So you can try out how much you know about data structures by doing the quiz. So that's quite useful. The link for the resources is in the PDF that we've got, but there's a link here as well. So you can grab it with git clone, and this gives you the git. There is nothing there at the moment, or very little there at the moment. The link is not browser. Sorry, the link is not browsable. Sorry, it's not that it is browsable. It's not browsable. Sorry, I was like talking to Patrick whilst writing that, and I made a mistake. See if I can edit that. Edit message. Link is. How do you edit a message? I don't know how to. Oh, there. Link is not browsable. Is not. So if you click on it, you're going to get a 404. The link is not browsable. All right, but you can say git clone and you get it. You don't need the sources for this course. If you want to see what I'm typing, you're welcome to take them, but it's not absolutely necessary. You can just watch. Everything's going to be inside the recording. All right, so what else do we have? Let's get started. So what I normally do with this course, first of all, this course is for you. This is your course. There's nothing that, like, I'll do anything that you want to talk about in the data structures of Java. So there's no such thing as a bad question. I'll deviate from anything to anything, no problem at all. Very, very happy to change. Yeah, grab yourself JDK 21. Whilst it's downloading, I'll continue talking and I'll just go through this. So what we've got with the data structures framework, we've got a bunch of interfaces. There are quite a few. Then we have a bunch of abstract classes in between the interfaces and the implementation classes. And right at the top, you're going to find iterable and collection. And iterable is a way to iterate over the collection. Collection is like the parent of all the different collections. So iterable is something we can iterate over, right? There's also an iterator, which I should have added in here as well, actually. Let me add an iterator here as well. Iterator is what we use to do the iteration. So there's iterator. I should pop these at the bottom. And there's also stream. So iterations and streams are both ways in which we can iterate over our collections and walk through them. So I'll put this at the bottom, right at the bottom. These are all interfaces. I think streams interface, if it's not an abstract class. Let me double check. Yes, interface as well. And but right at the top of iterable, which is something we can iterate over, we've got collection, we've got sequence collection. This is something new in Java 21. And the idea is with sequence collection that sometimes you want to be able to, you want collections to have a certain order, certain ordering. Like, for example, a tree set is sorted. An array list is ordered by in which order the elements were added in there. So you always have an order for an array list, a defined order by how you added the elements to the array list, and maintains that order. Whereas with the tree set, it's going to be, for example, sorted. So these are the root, and then you've got the list. The list is a list of items from 0 up to length -1. We've got a set which is just it's like a mathematical set with distinct elements. You don't know in which order they're going to be most of the time. It could just be jumbled around. They typically don't maintain the order, although sometimes they do. You've got then a special type of that called a sequence set, which does have some sort of ordering inside. We've got a sorted set and a navigable set. And then you've got queues. Now, the queues are not that interesting. Despite being in the list, they're not that interesting because queues, most of the queues are simply used internally within the within the JDK. JB, the course started about 5 minutes ago. So you're late, you're very late, but not too late. Just stick around and you'll have to be a part of this fun time today. So we've got our different queues. I'll show them, but there are quite a few interfaces: queue, blocking queue, transfer queue, deck, and blocking deck. And well, these are sort of interesting, but they're mostly used internally within the JDK. Then we've got map. We've got map and sequence map. And map is a one-to-one mapping between a key and a value. And you could say that the list is a one-to-one mapping between index and value. Right? You could have that mental model. You could say that with the list, it's like 0 through length -1 will get you an index to the elements, whereas here with the map, it's like any key to any value. And again, there's a sequence map. This is a new Java 21 interface. So for example, a TreeMap would be a sequence map because it has some ordering based inside. And then you've got sorted map and navigable map and also concurrent map. There are concurrent maps which allow us to have multiple threads using it. And the reason is that the map is it's very high probability that multiple threads will want to use it at the same time. Because quite often you'll use a map as a sort of dictionary to store some information, to put things there, to find them again. And so the concurrent map has also high probability of having multiple threads walk through it. And of course, you've got different types of ways of iterating through these things with an iterator, with a stream. These are the most common ones. And nowadays we use mostly streams, but sometimes also we want to use iterators. So that's the very high level view. We haven't gone into any details, and the interfaces define what we are going to be doing. Now, when Java was invented, which was Java 1.0, they only had interfaces, and interfaces couldn't have any code inside. And interface also couldn't have any state, and they couldn't have any actual implementation code. And so when they did these collections, there was Java 1.2 when they came. They wanted to introduce list and so on, but they wanted to have like a default implementation for certain methods. So for example, if you have a collection has a method called isEmpty. Now, how do you know if something's empty? Well, one way to do it is to look at the size and see whether the size equals 0. And if the size is 0, then the collection is empty. So, and so you could have a default implementation of isEmpty that simply says, size equals 0. That would be reasonable. But at the time, Java wasn't powerful enough to have code inside interfaces. And so they had to have a different layer in between the implementations and the interface for default implementations. This all changed in Java 8. So if you look at collection now, I think they've got a default implementation for, oh, they don't. So I thought they would have had a default implementation for isEmpty. It looks like they don't. isEmpty is still only abstract. But they do have an abstract collection, which is a partial implementation of any collection. And here isEmpty says size equals 0. So you've got that as a default implementation. Nowadays, what we would do is we would actually have a method inside. We would actually have a default method inside collection that says isEmpty and size equals 0. And they do use it to some extent. For example, let's look at the iterator. There's the iterator over here, and the iterator now has a method. The remove method has become a default method. It didn't used to be. And remove by default simply throws an exception saying, you can't remove. I'm very sorry. So this is how it works. You've got default methods nowadays in interfaces, but they didn't used to have that, which is why they've got this layer in between of abstract collections and abstract classes. Most of these do not have state. So abstract collection, for example, does not have any state. We have abstract list, which does have state. This one has a mod count field over here. So it's got a mod count field, and the mod count is used in order to see whether your collection was modified since we last created an iterator. And we'll talk about that in a moment, because this is how they do the concurrent modification exceptions. So that's the abstract list, the abstract map. I wonder if they've got any fields here. They have well, they've got these fields, key set and values. These are sort of optimizations. So they do have some collection. They do have some other fields as well. But for the default implementations, they wouldn't need to do that. They could simply have used interfaces and have all of the default implementations defined inside the interface. So we've got abstract map, abstract queue. There's also abstract sequential list, which only has one subclass. That's our linked list. So this is the layer in between. It's a bit old-fashioned. Nowadays, you wouldn't do that. So there's a question by NJ, the vid of the older version of the class. So if you go to the top here, there's this one here, this gift for you. Data structures, grab this. This has a quiz built in. Unfortunately, we don't have time to do the quiz during the class. I would love to do that, because that's really fun. But we wouldn't have enough time to cover all the material. One day I'll convert this to like 5 days. We'll have like a 5-day course with lots of questions. But for now, there's no time to do it. But if you grab that, you can do the quiz in there. And the quiz is quite nice, because it'll help you prepare for kind of harder questions. Anything you need to be careful of. Be careful of the following. I'm going to say that very few people will get all the answers right. Okay, very few people. I believe that they're correct, but very few people will get them right. So the problem is if you go for a job interview and they say, all right, Mr. NJ or Mrs. NJ, we would like to, let's ask the following question, blah, 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 blah. And you say, I know this one because I saw this in Heinz's questions, quiz, and you answer the way that I answered. They might think you're wrong, right? They might think you're wrong. So just make sure that if you answer, you probably want to say something like, well, I believe that the question answer you're looking for is, that's the answer. However, when I did Heinz's course, and you might have to say who Heinz is because they might think you're talking about ketchup, then I actually, I saw that this is, that he said this is the answer, and here's the reason why. I've got a separate course, which I'm not going to give you, where I have a walkthrough of the quiz, where you can see exactly why I've got the different answers. But you can always ask a question in the comments of the course, and I'll gladly explain why a certain question is the way it is, or answer is the way it is. So I'm fairly confident. I wouldn't bet my house, but I definitely would bet a beer that the answers are correct. All right, so we've got the interfaces at the top, then we've got the abstract classes in between, and then at the bottom we've got implementation classes. And you can even say there's an abstract sequential. Oh no, so this is our old abstract sequentialist. All right, so you'll notice that they've got the there's the sequential collection, right? And there's no abstract sequential collection, because if you look at abstract sequence, or if you look at the interface, the modern interface, the sequence collection, that's what it's called, they do have the methods implemented with default methods. So by default, add first, add last will throw an exception. Get first, get last throws an exception. Remove first, use the iterator to remove the first element. Remove last reverses the iterator and uses that to remove the last. So what I'm saying is that the sequence collection does have most of the methods implemented already, and just adds one method called reversed, which we have to implement. Yeah. Okay. So let's go on. Where are we? Let's go back to my code. So what we've seen so far is just the interface, and that's what we're coding to normally. So normally when I've got a field, I'll use a field as I'll use an interface as a field. For example, I say private final list of employees, for example. So employees equals new array list. So this is how I would normally go about writing my list. I wouldn't go and say array list employee equals employees. Let's create this class, create an inner class employee. Okay. So that's how I'd normally write it. I wouldn't say array list employees. And so when you're defining your field, normally you have rather a very high level list than for example a concrete type. You wouldn't have an implementation class. You normally wouldn't say array list over here. You'd say list or even collection. Say collection of employee equals new array list. And that will give you everything you need in order to use that list of employees. But here are the different ones. There's ArrayList, which is the most common one, not thread-safe, array-based class. There's a CopyOnWriteArrayList, which is array-based, but it's thread-safe. There's the LinkedList, which we don't really use. There's a stack. Vector, these are very old class. You wouldn't use these. And then there's an immutable list called list of 1, 2, 3. List of, which is immutable. And the ones you use most often is the first one and the last one. These are the ones we use almost all the time. The ones in between, we will use rarely. So I'm going to say this one, you can use 99% of the time, or 90% of the time. This one, maybe 0.1% of the time. Linked list, never, 0% of the time. Stack, never, use a decorator, the vector. Rarely, I'm going to say 0.01% of the time, and the rest would be like 9% of the time would be your list. In fact, 9.9% of the time. So most of the time you'd use these, the first one and the last one. Okay, and then for sets, you've got your hash set. Hash set is it's an array-based list set, and it uses, if you have a lot of clashes, it uses the red-black tree. We'll talk about all of that in a bit. We use that quite a lot. We'd rarely use a CopyOnWriteArraySet, only for very, very small sets. The LinkedHashSet, maybe you'll use. There's actually a place that gets used within streams. I'll talk about that. And then EnumSet, like hardly ever. Immutable set I use fairly often, actually. So most of the time, you're going to go to. Not so much. We should have this. I'm actually on the carbots branch, but the master branch should have this as well. So this code here. Oh, I'm sorry. You're sorry. Okay, you're looking at the wrong thing. Cool. So this code should be there. Should be everywhere. Then you've got the TreeSet, which is sorted, and the ConcurrentSkipListSet, which is also sorted, and ThreadSet. All right. So these are the sets. Then you've got queues, a bunch of different blocking queues used for thread pools. The transfer queue, which is never really used. It was built for a very specific purpose, but never used in that purpose in production code. So then you've got the array deck. This is pretty cool. It's not thread safe, but it's like a stack, double-ended queue, and the concurrent link double-ended queue if you need that. And you've got the link blocking deck as well. So as I said, I don't want to emphasize the queues because they are not used that much, but I'll gladly answer questions if you have any about them. We have a bunch of maps. The most important is your HashMap and your ConcurrentHashMap. These two are the most important. And I'm going to say that the ConcurrentHashMap is a little bit more important. You might do map off, not that often. And if you need thread safety and sorted, you can take a ConcurrentSkipListMap. If you need it sorted but not thread safe, you can take a TreeMap. And that's basically all there is to see. There's not that much in terms of richness. They've always been very hesitant to add new implementation classes to the collection framework. So this gives you a good starting point. I actually normally manage to do almost everything I need with these collections. There are other collections like Eclipse collections that expand on this and add lots of other types of collections. But in most cases, this is actually enough. All right. Good. Any questions, please ask me. So when you talk about data structures, it's always important to ask how expensive are they to do different things with, right? So for example, if you have a collection, let's say I have a collection over here. In fact, I'm going to over here make a test method that says new array list. Okay. Then this test method is going to over here have just this be collection of integer, and will this be integer over here? And then what I'll do is I'm going to say naught up to 100,000, 10,000, inst.add. So just put an element in there. And then what I want to do is I want to, for example, find a particular value in that collection. Now, I'm going to look for a value that's not there. I'm going to say, if inst contains, I'm going to give a number that's not there, that's not going to be there. There's no string called not there. It's only integers. then throw new assertion error. Assertion error. Okay, didn't find it. And what we want to do is to measure how long it takes to do this. We're going to do this several times, not just once, because doing it once will be probably quite fast. We're going to go and do this 10,000 times, 0 to 10,000 times. We're going to see is it there or not. It's not going to be there, so it's going to run through 10,000 times. Okay. So let's run this code and see how quick that is. So for the first one, just for an array list, we're going to put 10,000 ints in there, check whether a string is there, which is obviously not there, and then see how long it takes to do that 10,000 times. And it takes half a second, which is quite long for what we're doing. So we're going to bump this up a bit. We're going to make it 20,000 and 20,000. So we're going to double in both directions, and then see how long it takes to do that. And we're going to expect it to be about 2 seconds. So then everything times 4. It's 1.5 seconds. And what we'll also do is we'll, at the top, we'll print out, or down here when we print out the time, we'll say ints.get class.get simple name, which is plus time, so you can see what the actual class is. So first it's going to be ArrayList, and what we'll do is we'll run this whole experiment a few times, 0 to 10. Let's put ArrayList in there. We'll then do a new LinkedList, which I said don't use, but let's try it out. We'll try HashSet, and we'll try a TreeSet. Now what I'm going to do is I'm going to change something here. And yeah, so exactly. So JB is on the right track there. And just want to change something to always use java.util.star for imports, because otherwise I'm going to go nuts. You don't want me to go nuts, do you? No, I know you don't. So we're going to say that for use star with input java.util.star, and also Java concurrent star. And the reason is that once, with subpackage as well, because I didn't need that because it's with subpackage already. So I can delete that. Because otherwise what happens is that, you know, the moment I import one util, I'm going to have more than one util. So I'll just for this course, be easier to do this way. So this one, let's try the copy on write array list and array set, and let's do an array deck as well. So we'll run this code and you'll see all the different answers here, different times. And of course, it's going to be much faster to use a HashSet or TreeSet than to do this with an array list or linked list. And the reason is that when I say contains, oh, okay, that didn't work. So with integer, of course, it fails because it's trying to do compare to between integer and string. So we'll have to do an actual integer here. So let's change it to be something which is not there. So the bigger the list, the longer it takes. And you can see that we'll let it run through once, and then we'll run through it again. So after it's warmed up a bit, it's about 1 second for the array list, about 3 seconds for the linked list. HashSet is so fast, it says 0 milliseconds. Because with HashSet, it's not so much dependent on the length of the size of the set. It's more the quality of the hashing that makes a difference here. It seems to have stabilized. We're looking at about 1 second for ArrayList, 3 seconds for LinkedList, because it's linear cost, and it's linear to the size of the list. So if I go and change this to be only 10,000 elements, it needs to look through, you're going to see that it's going to be roughly twice as fast for the ArrayList. Well, that's of course a linear cost. If you, but sometimes if you do algorithms, you might end up with a quadratic cost, order n squared. Right. That's more problematic. Quadratic cost is definitely worse. So the HashSet's very fast, TreeSet's very fast, other ones are very, very slow. So this is the linear cost. If you double the size, it becomes twice as slow. But with the HashSet, it doesn't. It stays roughly the same speed. And there are lots of examples where you have strange complexities. O1 is constant time, that's like your HashSet lookup. It's supposed to be ON is your linear lookup, that's your ArrayList lookup. N squared is something like contains all. Right? So what we'll do is we'll do, oh, this is 10 times, so 3 times. If you do the following, if you say ints.contains all ints, right? So it does all contain itself, and if not contains all, then throw new assertion error. Right? We do a time on that as well. So time contains all time. I'm going to just change this a little bit. Put this one first. There's the print line at the top to print the name up front. And then we'll have over here just the time. Like that. And that one is the contains time. So contains time is going to be proportional to the length of our collection. So if I run this code now, you'll see that contains all is going to be quadratic. So if you look at contains all, it's 183. Okay, and if I double the size to 20,000, I'm going to just comment out this one for now, first one. If I double the size to 20,000 of 183, it's going to be roughly 4 times as slow. CopyOnWriteArraySet is going to be a problem. I'm going to comment that out because that's a very slow class to use for anything that's a bit larger. You see that the ArrayList is roughly half a second. If I double it again, you're going to see that the ArrayList is going to be, again, quite a bit more expensive. We just have the ArrayList, the ArraySet, and the HashSet and the TreeSet. Double it again, and instead of getting twice as slow, we're going to become 4 times as slow. Do we need the 4 at line 31? Oh, have a look. Okay, I'll check that now. So we'll see the ArrayList, we double it, becomes, again, 4 times as slow. But the other ones don't degrade like that. The other ones will be much better than that. So let's make it 80,000. Okay, so the reason I did the for loop here is that a single contains is quite fast, and you wouldn't actually be able to really see the time if you just looked at that. So run it again, and now it's going to go to 8 seconds from 2 seconds, roughly 8 seconds. So quite quickly, we get to a stage where it's intractably slow. But the other two are fine. They behave quite well. Okay, and I'll point at a few of these ones, especially the n squared, order n squared. It's very problematic because you can imagine you're happily running along, and your code worked fine for cases where n is sort of 100, but suddenly n goes to 100,000 and becomes very, very, very slow. An example of that is bubble sort. Bubble sort is n squared. Bubble sort is absolutely fine when you've got a very small collection. If it's like 10 items, then bubble sort's okay. But as the size increases, you end up being extremely slow in comparison to everything else. All right. Log n is logarithmic. That's what your tree set's all about. And you could see here at the output that the tree set doesn't degrade very much. It becomes a bit slower, but not that much slower. Because if you double the size, you're just going to have one more step to go. So logarithmic is really very, very good. And then n times log n is what your typical sorting function will take. So if you have, for example, merge sort or quick sort, it's typically going to be n times log n, unless you're unlucky, in which case it'll be much worse than that. All right, so this is the foundation. Most of the data structures books would start with something like this to look at the computational time complexity. And we normally use O1 for constant time, On for linear time, On squared for quadratic time, which you don't want to go there. I'll show one example that will amaze you. Let's make a record pixel over here, position, int x, comma, int y. I'm going to do the following. I'm going to say, make a list, make a set of positions, make a list of positions. So I'm going to make a list of positions equals new equals the array list, and going from with x from 0 to 100 and y 0 to 100, we get 10,000. We're going to say positions dot add new position x comma y. And then we're going to measure how long it takes to put these in, to make a copy of that as an immutable set. So the classical way of doing it is to say set dot copy of positions. Okay. This will be immutable. So this is a very common approach to this way. And so this is 100 items, 10,000 items. And what I'm going to do is I'm going to measure the cost of this over here. So I'm going to just put a timer on that. That is the immutable set time. And I'll call that a few times because the first time it will still optimize the code. So we'll just do a for loop around there. A for loop int I equals 0, I is less than 3, I plus plus. And then we'll see the time with 10,000 items. And you see with 10,000 items, it's already half a second. So it's very, 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 very slow. I mean, to construct a set of 10,000 items should be almost instantaneous. If I make it 20,000 items, so 200 by 100, watch what happens. It goes from half a second and bumps up to 2 seconds, almost 2 seconds. So what does it tell you? It tells us that the copy off is a famous quadratic, possibly quadratic performance. So it might be. So maybe quadratic. Okay. Doesn't have to be, but it can be. Not getting video, please refresh. Most likely you need to refresh if you're not getting video. If you're the only one screaming, refresh. Okay? Always try that first. Always try refresh first, and then if that doesn't work, then you complain about the video. All right. Now, just to mention that when you're storing items, storing them inside an array is normally more efficient than inside a sort of node-based linked structure. And this is also why when I did the test early on, the linked list was so much worse than the array list. What happens with the linked list, you've got lots of links in your list, each pointed to the next item. And so it takes a lot more memory. And the items are, the elements are distributed throughout your memory. Because of that, the linked list is a lot more expensive to create and to maintain than an array list, which is simply one big array and everything is inside there. At the moment, Java does not have the option of storing items inside primitive arrays. See, if you do, for example, this, if I say int array numbers equals, let's say int stream, factors to this, let's make some random numbers. Got a million random numbers here. So we're going to say thread local random dot current dot ints. We're going to make simply 1 million random ints into an array. Okay. Then we're going to, and the size of this array is going to be very easy to determine. It's going to be 16, which is the object header for the array, plus 4 for the size. 12 plus 4. 12 is object header plus 4 is the size, plus 1 million times 4, because it's 4 bytes per int, gets you the grand total of 4 million and 16 bytes for this array. And that's it. It's all one contiguous place, one place in memory. If I do this with an integer array, so I'm going to say integer. I'm going to say after making this, I'm going to say int stream dot off numbers dot boxed dot to array integer array new. If I do that, this will be numbers 2, numbers 1. This is going to use a lot more memory because what we've done is we've boxed all of the ints to integers, right? Integers numbers 1. So it's going to be 12 bytes for the object header plus 4 bytes for the length. Plus, we're going to have 1 million pointers times 4. That's the pointers pointing to the numbers. But each integer can take up to 16 bytes. You're looking at, again, 1 million times 16. So you're going to get to 20 million and 16 bytes for this. And of course, it's far more compact to store everything in primitives. Unfortunately, Java does not have an option at the moment of storing, of having data structures with primitives. They are working on that, but it's not available at the moment. How to get to 4 million and 16? 12 plus 4 is 16, plus 1 million times 4. It's 1 million ints. Each int is 32 bits, which is 4 bytes long. That's how you get that. And with the second one, it's going to be the int-array boxed, that's going to be integer array, and it's going to be 12 times 4 for the object header and the length. 1 million pointers, 1 million integer objects, comes to 20 million and 16. And then if you convert this to a linked list or to an array list, the array list will be almost the same as the array. A little bit more, but not that much more. But if you make a linked list of integer number 3, each link in the node is, I believe, 24 bytes. Yeah, so KP, I'm assuming compressed loops on this, and I'm assuming we don't have project Lilliput yet. There's a project called Lilliput, which is to compress the object headers to be only 8 bytes instead of 12 bytes per object. At the moment, we don't have that. I'm also assuming not Project Valhalla. So then we're going to be able to compress this even further. So this is the current, right now, Java 21 compressed loops. The padding for word boundaries, you're looking at 8 bytes padding, but that is anyway a multiple of 8 bytes. So that's correct. So if I make a linked list, within the linked list, you're looking at, for this, we've got a node. Each node is 12 bytes for the object header, plus 1, 2, 3 times 4 will give you 24 bytes. Now there's a great plugin called JOL, which I've got installed here. If I can right click on this and say show object layout. And it shows me, this is exactly 24 bytes with compressed loops. If I have a 64-bit hotspot, 8-bit alignment, and compressed loops, that's what the default is most of the time, then that's what the size is going to be, 24 bytes. So if you go and use so this is really recommended, JOL, if you're doing experimentation, it's a great tool to use. So for the linked list, it's going to be roughly this. So if I say stream of numbers to dot collect to collection linked list new. Okay, so this is how we collect it to a linked list, and this is going to be. I'm not sure how big the linked list is by itself. We can easily look that up. Just go right click and show object layout. 32 bytes. So that's 32 bytes for the linked list, and it's going to be there for 32 bytes plus 1 million times 24 bytes, because each node is 24 bytes. So with the linked list, we've got all these nodes pointed to each other. You've got the first one, the last one, and there's like a long linked list in between, and then each of them is also going to point to the integer object. So you're looking at times 16, so you're going to be 40 million and 32. So that's the size you're going to have for a linked list of that size. All right. Okay, so this is what we get to, and if we do the following, if we make an array list of integer numbers 3 is 4 equals, I'm going to pre-size it to the right size, which is going to be 1 million elements in here. Oh, see, my coloring is being adjusted automatically for me. Oh, it's not. Got an app on my phone to do the color correction. The camera's fighting with me at the moment. It's angry with me. So it's like, I'm going to fight with you. So I make 1 million elements in there. Well, I could actually just say pass in here the linked list. It's even easier. Number 3. Then it should be pre-sized to the correct size. All right. The array list is going to be very close to the integer array. It's going to be, again, we're going to, if you look at the actual class, the ArrayList class, it uses, so 24 bytes, 40 bytes, or something like that. 24 bytes for the array list. Here, instance size 24 bytes. So you're looking at 24 bytes for the object header in the class, plus the integer array. So it's plus integer array that we had before gets me to 20,040,000 bytes. And that's it. It's very close to the integer array. So, I think I know who KP is. No, that makes sense. The question starts to make sense. Otherwise, the question doesn't make sense. Hello, KP. Hope you're doing well. All right, so if I now sort these things, you're going to see different performance for the sorting. So we're going to say arrays.sort numbers 1. Oops, do that. Again. That's time 1. I'm not going to do any warm-up here. Then I'm going to do numbers 2. Then we're going to, now we can't do array sort on the 3rd and 4th. We need to do that directly. We're going to try numbers 3.sort. Now, that's going to be our time 3. And lastly, the numbers 4.sort. Numbers 4.sort. Now, it's the array list sorting, and that's going to be time 4. Obviously, we should be warming this up. So let's take the whole thing and put it into a method test, and we're going to simply call that 3 times. Run, and we'll see how the performance goes. Okay. Yeah, I always do it in milliseconds. So that's why it's time divided by a million. Thank you. Thank you. Thanks very much. That's very helpful. Having such clever people watch us is very helpful. Okay, let's do that. Let's run that again. Thanks, you1. So you can see that the time 1 is very fast. Time 2 is a bit slower. And you might wonder why 3 and 4 are, well, 2, 3, and 4 are going to be similar times. I would expect time 3 to be a little bit slower because it needs to make a copy of the entire array before it sorts it. But you can see that 200 milliseconds versus 1.2 milliseconds. And there are several reasons for that. First of all, it's a different sorting algorithm. And secondly, it's also, it also uses a lot more memory, which it has to navigate. Let me just quickly reset my camera just 1 moment. It seems to help if I turn it off and on again for some reason. And hopefully we'll sort it out. It doesn't give us problems anymore. Okay. All right. So there we go. Lots of fun with this one. And the memory use, of course, has a great effect on that as well. Now, most of the time, what we're going to do working with is lists. And there are different ways of creating lists. You can do this. You can say arrays.asList 1, 2, 3. And this has been a sort of a very common way of creating a list, arrays.asList in the past. But we shouldn't use that in future. Right? Because when I say arrays.asList, as list takes a dot 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 varargs argument, so t dot dot dot, and what it does is it creates a wrapper around this array that's inside here. So if you say arrays as list 1, 2, 3, this is relatively benign. I can say over here my list, but I can't add an element. I can't say add 4. That's going to give me an exception. But I can change individual elements. And so it seems like an immutable list, but it's not an immutable list, because I can say list.set 0, 4. And therefore print out the list, you're going to see that it's going to be the wrong answer. It'll be 4, 2, 3. Well, not wrong, just change answer. But it gets worse than that, because this is simply a wrapper around whatever you're passing in here. If you convert this to an array, let's say over here, for example, object array data equals 1, 2, 3, then I pass that into the as list data. What is that? Oh, it must be integer. Let's change integer. So then I can still change it the way I did, but it gets worse, because if I change the outside array, it also changes that as well. So if I say data naught equals 42, it's also going to change the list. So it's a fairly dangerous thing to use, and a much better approach going forward is to use list off. So that's what we should be using going forward. So we have, instead of doing it this way, we say list.off data, and list off has a dot 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 parameter, so it's the integer elements, and if I try say set, it's going to give me an exception, unmodifiable exception. And if I change the outside array, it doesn't have any effect on what's happening inside. So if this won't work, which is what I want, and if I change the array outside, it doesn't affect the integer, the list I've created. So going forward, don't use arrays.asList anymore. Instead, use asList. Now, there are lots of methods on list. I'll go into those quickly. So we've got over here add, contains, etc., etc. Sort is part of list now. And we'll get to that in a moment. What sorting is, why they've got sorting in there, and also reverse is also part of that now. But we'll talk about that as well in a moment. But also there's a thing called random access. Random access says that you can access an element in the middle in random time. All right, so NJ asks, why is it dangerous to use arrays.asList? The reason it's dangerous is that it seems to be immutable, but it's not. It gives us this false understanding, this false feeling of being immutable. But it's actually worse than, for example, arrays, the normal array list. Because the normal array list, if the array list doesn't have a holder, doesn't have a pointer back to anything outside. So if you change what's outside, it won't affect what's happening inside the array list. But with the arrays as list, it's simply a wrap around an array, and if that array changes, then you're changing the list as well. So it seems like immutable, but it's not immutable. So rather take something which is immutable, like list.off, and use that instead. All right. So the only class that's not only list which is not random access is LinkedList, and so we shouldn't be using that anyway. But this just says that you've got a constant time lookup into the middle. All right. We actually on top of the hour, so we'll take a short break here. Let's take a 7-minute break. When we get back, we'll look at ArrayList a little bit more, There are a few things we need to know about remove if, and the size is important. We don't want to waste too much space, but there's lots more to come, and I'll see you in 7 minutes from now. So I'll put the timer on, and we'll be back in a few minutes. Okay, so shall we continue? All right, so ArrayList is an interesting one because what happened, the way it works, is if I, let's go to JShell from that. When I construct a new ArrayList, it's going to initially not have a size, right? Or the array inside is not going to be of any size. The moment I add one element, and this is the current implementation you'll find from Java 7 up to Java 21. When I add one element, it's going to initially start with the size of 10. Once we reach the size 10, well, once we exceed size 10, it's going to increase the size by 50%. And then once we exceed that size, again, increase it by 50%. And it keeps on increasing it by 50%. So if I want to add 1 million ints to an array list, one at a time, every time it runs out of space, it increases by 50%, starting at size equals 10, or length equals 10 rather, length equals 10. I run out of space, and I'm going to say length times equals 1.5. That's the first time. The second time, the third time, the fourth time, the fifth time, 6, 7, 8, 9, 10, 11, 12. And these are all arrays which are being constructed, and they're going to be thrown away once we run out of space. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 already, 25, 26, 27, 28, 29. And we've gone past the million. So we've managed to get past the million with about 28 resizes. And but you see that there's a fair amount of fluff here. So there's the actual size of the array is like, it's not 1 million. Where was it? Was here arrays? It's not 1 million, but rather it's 1.2 million. And you can see that if you go to ArrayList, and let's make a list here. We're going to say list of integer, list equals new ArrayList. And we're going to say from 0 up to 1 million, list.add I. And we're going to print over here the length, and we'll set a breakpoint at that point, list.size. Size is going to be exactly 1 million. But what we're going to see is when we debug it, we can look at the actual length of the underlying array. So run it. When the breakpoint hits, if you click on list, it's going to say 1 million, size 1 million. But what we actually can do here is we can say right-click and view as object. View as object. And here you can see that it's actually an element array, object array. And it's exactly what I had in JShell, which is 1215487. So it's exactly the same number there, 1215487. There we go. That's the size of the underlying array. It's quite amazing. And that's quite incredible to have that. Now the problem is that, well, what we could do is we could start off by saying 1 million. Then it's always going to be the right size. Or after we finish constructing it, if we make this an array list, we can say list.trim to size, then it's also going to be exactly 1 million. So U1, yes, I am of course going to just commit my changes to get afterwards. I'll do that then. I won't do it right now. I'll do it later. So the problem with this is that actually, if I construct this from a stream, which probably we should be able to use a stream for this. To just say this, instream.range.box.collect.collectors.toCollection. By default, if I just say .toList over here, in fact, this toCollection ArrayList, Let's do it like this. Let's make it a list. Just say to list. We've got the same behavior where it's the wrong. It's a much larger array than we actually need. It's 20% more than we actually need. So that's another whole bunch of bytes wasted, this empty space, which we don't actually need. I don't recommend that you simply, everywhere where you're doing this, that you would go and trim to size. And the reason is that there is work in progress to eventually get rid of this extra space. And there is work in progress that one day, what's hopefully going to happen is that when an object is ready for garbage, or not for garbage collection, once it goes from the young space to the old space, or after it's survived a certain number of collections in the garbage, in the heap, that it will automatically be trimmed to size. So that's something which is happening. That's what I'm saying. I wouldn't go and trim to size up front. If you want to prevent the 28 additional collections, or what you can do is you can over here say collectors.to collection, and you can say new ArrayList of the right size, and then it's going to be the right. But it's a lot more clumsy. It's not so pretty to do it this way, but it will prevent unnecessary expansion of your array list. Right, that's the first thing. The second thing is that let's say that I've now made my array list, and I've decided I want to remove all the even numbers. So I'm going to say itco and iterate over here, and I'm going to say if next %2 is 0, then iterator dot remove. We have to remove all the numbers which are even. Okay? And we're going to measure how long it takes to remove the even numbers. It should be very fast because there's only 1 million elements. It's not that many. Okay, it's taking longer than you think it should. So why don't we do this? Why don't we change it to being not 1 million? Let's put here size and size. Let's decrease it to 100,000. So doesn't take that long. It's a lot faster. Wow, so 100,000 takes a whole second to run. That's quite slow. Let's do it to 200,000, see how long that takes. So double the number, the size, and it becomes 4 times as slow. So what does that tell you? It tells you that this loop over here is actually quadratic, because when I remove an element, everything on the right-hand side gets shifted 1 step to the left. And so because of that, you end up with it being quadratic. If I make it now 400,000, you're going to be roughly 16 seconds. It'll be 15 point something, but it'll be in that order. Luckily, there's a solution, and that is to remove f, which is a very clever piece of code. And what we can do, instead of doing it this way, which takes far too long, who's got time for that? So almost 16 seconds. We can change this to be to use remove if. And IntelliJ even suggests it for you. It says replace with remove if, and we simply pass in a lambda that is going to say, or a function here, if it's even, then remove it. And now it goes from quadratic to being linear to the size. So 400,000 completes in milliseconds, very, very fast. Let's make it a million again like we had before. Oh, if you want to extrapolate how slow it would have been to go to a million, we had 200,000. We had 200,000 took 15 seconds. So 400,000 would take 60 seconds, 1 minute. 800,000 would be 4 minutes. And a million would be a little bit more than that. So maybe about 6 minutes, 7 minutes or so. So a very long time. All right, so we can see here that it becomes a linear cost rather than a quadratic cost. And the way it works is quite clever. When you say remove if, it actually, okay, that's not what happens. You need to look at ArrayList. What it does is it first of all starts looking and tries to find an element to remove. So it just runs through until it finds a first where it needs to remove it. But then what we do is we go from where we found the first one must be removed, and we make a death row, that's a long array, of all the bits from there until the beginning, from the number of bits. And we then mark all the elements which must be removed inside this bit set, this long array. We do that over here. We iterate through with the rest of the elements to see which ones need to be removed. And I think it starts at the beginning and goes to the end. That's right. I would be. Oh, okay. This is from there to okay. And then what we do is we go through a second time, and we simply do something like, we call that a rabbit and hare type of, sorry, not rabbit and hare, tortoise and hare iteration, where we're running at different speeds. On the one side, we have W, which is the tortoise walking slowly, and it's incrementing, setting to the next item in which hasn't been cleared. Then last we shift the tail over the gap. So it's very clever, and what it does is it gives you an order n performance of removing a whole bunch of elements. All right. So the most important things here with ArrayList is the size. Starts as 10, basically, increase by 50% every time you run out of space. And if you can help it a bit by pre-sizing it. And then also be careful of remove if, because that's, well, not remove if, removing with an iterator, because that is quadratic. It's better to use remove if. ArrayList is also not thread safe. So if I have multiple threads using one list, things are going to get ugly. So if I make a list of, well, let's just take a list over here. Let's do this. We're going to say integer dot instream dot range 0, 20. Let's 20. Let's make it 1,000. Dot parallel. Dot for each. For each I, I'm going to say list dot remove if. I'm going to say add. How about the list dot add I? Okay, so I've got 1,000 parallel streams, or 1,000 up to 1,000. Let's make it a bit more. Let's make it 1,000,000. Adding like this. So adding with multiple threads to the list. And we started with 1,000,000. If I now print it afterwards the size of the list, it's going to be like, could be anything. Because it's not thread safe, so you're going to have a probably corrupted list of them. So the list of size is apparently 770,649. It's not going to be 2 million. In fact, it's smaller than 1 million. Oh, actually, it should be smaller because we removed half the elements. But yeah, so it should be 1.5 million. That would be the correct amount if it wasn't in parallel. If you take away the parallel, do one thread, then it's going to be 1.5 million. But multiple threads removing it or adding at the same time is going to have race conditions, and they're going to overwrite each other's work, and you're going to get garbage out of there. So be careful, it's not thread safe. Not thread safe. If this were a vector, it would work. So I'll copy this to the vector just to show you that it would work. Now, we don't use vector that often. I haven't used vector for a long time. But this would work with a vector. So I'm going to copy and paste this. In fact, why don't we do this? We'll say, I'll just change to vector. I'll show you. Change it to vector and run it. Then it should work to have a whole bunch of threads adding at the same time. That should run one correctly. But it's very seldom that you'd need this behavior. That's why I say most of the time you don't use vector. Vector is not deprecated. It's not a deprecated class. It's just that most of the time we don't need thread safety with lists. But if we do, then vector can be your friend. Okay, so let's change it back to ArrayList, because that's what we really want to do here. And I'll comment this out again, because that's not correct. All right, if you have any questions, please feel free to ask. The other thing is iteration. Most of the iterators are either going to be fast fail or fail fast, or they're going to be weakly consistent, one of the two. And so the demo that I normally show here is I start with the vector. Vector is a very old class, and I want to show you what happens if you iterate over the vector. Now, this is going back a few years, Java 1.1 or 1.0 when I started coding in Java. And I've got a vector over here. I've put a bunch of beach toys in there. There's a floaty, a sunblock, rage, razor, umbrella, bucket, and raki. And you wonder, why is rage, razor, and raki on the beach? And I must confess that for the last 3 days, there's been raki on the beach. My friends, we hang out on the beach. Well, they hang out on the beach. I go for my running and my exercising, but they hang out, and there's been lots of name days. So there's been lots of raki on the beach. But normally you don't have that on the beach. That's an unusual situation. So I want to remove any item that starts with RA, including rain. If there was a rain, I want to also remove that as well. So we're going to say, now, before we had iterated, there was a thing called enumeration. So let's write a for loop, enumeration of string, let's call it iter, equals beach toys dot elements. That's what you used to use for iterating through these things. While iter dot has more elements, was a bit longer than has next. And then what we did was we would say string toy equals iter dot next element. So if I say if toy dot starts with RA, and I then say beach toys dot remove toy, what would happen when I print out the beach toys? That's the question. What do you think? What do you think will happen if I run this code? This is now with enumeration. It's not iterate, it's enumeration. It's Java 1.1. So if you know the answer, pop it into the group chat, and we'll compare the answers at the end. There's this bit of a time delay from when I speak until when you hear me. It's not real time. It's like a half-minute delay. All right, let me run it, and we'll see whether it's correct, whether it matches what you think it would do. So if you run it, you'll see over here that it actually outputs floaty, sunblock, razor, umbrella, and bucket. Oops. Not quite what I thought. Why is there a razor on the beach? We don't want razors on the beach. that's definitely not the right thing to have on the reach. And what happened here was the razor, when we removed rage, razor took the place of rage. And we then advanced one step. We saw umbrella, we didn't see the razor. We skipped past the razor. This was a mistake that a lot of people did, like over and over and over again. Exactly, it skipped the element. This is iteration. Let's call it demo 1. Okay, so that's the first demo. Now, a second way to do it, or what I would do in that case, when I used to write with use vector, I did the following. I said, instead of simply saying remove, I would say vector string to remove equals new vector. And then I would say, instead of removing it, I'd say to remove dot add the toy. And then once it was done, I'd say beach toys dot remove all the to remove. So that's what I did. And that would then give me the answer you'd expect to see. Okay? It worked fine. It only had the toys not starting with RA. Cool. Now, the problem is that most of my colleagues didn't figure that out. Yeah, exactly. There we go. Move on. Thanks, Johan. We're thinking alike. But our colleagues didn't think like that. So they kept on making this mistake, and I'd hear them cussing down the corridor. So guess what? They've again forgotten this one. And so what they did was, when they added Java 1.2 iterators, they decided to make this a bit more robust with iterators. So instead of having just enumeration, they changed it to let me take not this one. I'll take demo 1 as a, so the original one I'll take as a basis. And what would now happen is they change it to iterator. Instead of saying has limits, it has next. And then it's just next over here. And this time, if you, it's iterator. This time, if you ran it, instead of just giving the wrong answer, it would actually do a concurrent modification exception. Right? So it would complain. So that's pretty interesting, isn't it? However, what you could do then is you could go and say remove it with the iterator. So you can say over here, iterator dot remove. So this one, iterate, this demo 3 is an example of a fast fail iterator. That's fast fail iterator. And this is the same for vector. And for ArrayList and for LinkedList, they all are fast fail iterators. And of course, nowadays we don't really use vector very much, so you just make it an ArrayList. ArrayList over here. There. And it will work nicely as well. And if you take, for example, a different type of list, for example, the CopyOnWriteArrayList, then that would not be a fast fail iterator. That would be a let's make this a collection rather. Collection. That would be a snapshot iterator. So CopyOnWriteArrayList, and this would work. Would this work actually? I'm not sure if this would work. Remove demo 4. Let's run demo 4. Not sure about the iterator.remove. That works on the CopyOnWriteArrayList. We can just remove it from the collection. No, that won't work. Didn't think so. But what we can do with the CopyOnWriteArrayList is we can say, just remove it directly from beach toys. So we can say beach toys.remove, remove off the toy, and you end up with it working correctly as well. Because you're removing from the snapshot or from the original, but the snapshot stays the same. Right? It's quite nice. All right, now, so CopyOnWriteArrayList is a snapshot iterator. Snapshot. The ArrayList would be fast fail or fail fast, giving a concurrent proliferation exception. And there's a third one called weakly consistent. So let's do demo 5 over here. And I'm actually going to use a sequence collection here. Sequence collection. Beach toys. I'm going to use a concurrent linked queue. Deques, actually Deques is better. And this is going to be weakly consistent. I'm going to add all the elements into that, iterate through, and remove the toy. Now, what I'm also going to do with the beach, with the snapshot, before I do the weakly consistent one, I'm going to say that if toy.equals sunblock, then beach toys.add rabbit. Okay. And what you'll see is that the rabbit will be there inside my list. Because I'm iterating over the original list, I'm not seeing the rabbit that was added later. Okay. I'll do something similar in here. I'll say that if the toy equals sunblock, add rabbit. Okay. This with the concurrent linked queue. And when you run this code here, let's do the demo 5, set it to demo 5. If you run demo 5, then what happens is it's going to delete the rabbit, because the weakly consistent will still see items added after where we are. It won't go back to what was before, but if you're busy iterating, it will see whatever is added afterwards. So if I say, for example, let's say add last rabbit, and if toy equals umbrella, then so make it rabbit 2 and rabbit 1, add first. You'll see the rabbit 1 will stay there because it's at the beginning and we've already passed that. There's rabbit 2, it's going to be at the end, and we'll remove that. So it's rabbit 1, floaty, sunblock, umbrella, and bucket. This is weakly consistent iteration. I've written a newsletter about that. I actually spent a fair amount of time looking at it because I thought, not many people have really figured that one out. When does it work? When doesn't it work? And if we can show that to you. So look at all the possible combinations of weak consistency, and it's there. See it over there. Weakly consistent iteration. So within that, you can see exactly which of the different collections have weakly consistent iterators. And it's basically, if something has a concurrent collector, or concurrent split iterator, you can know that it's a concurrent iterator as well. The problem we have in Java is that there's no way of knowing which iterator is weakly consistent and which is a snapshot and which is and which one is a fast fail or fail fast. There's no characteristic with the normal iterator. But there's a class called split iterator, and split iterator does have a characteristic. So if I say, for example, new ArrayList, and I say dot split iterator dot characteristics, then I can find out exactly what characteristics this ArrayList will have. So this will be, for example, ordered and sized, subsized, etc. And if I see that a split iterator is concurrent, then it means it's weakly consistent, and its iterator will also be weakly consistent as well. That's how you know. But there's no way of knowing if something's a snapshot iterator or if something's a fast fail iterator. Those are not part of the characteristics. I showed you the CopyOnWriteArrayList. It is a fairly complex class. Actually, a while ago, I wanted to do like a tear down. You know, when they buy an iPhone and they break it apart, they look inside what's inside the iPhone. Well, I wanted to do the same thing for the Java concurrent classes. The motivation was that why don't we like really dig into it, see how it really works inside. And unfortunately, I made two sets like that. One was on array blocking queue, and it took like 4 hours to break it down and look at it. The other one was on CopyOnWriteArrayList and ArraySet with great detail. Again, it took about 4 hours. And I made these amazing courses, really, really fun. And not enough people wanted to buy them because it's like very detailed information you won't find anywhere else in the world. But it just wasn't something that people wanted to buy. So I give it away as part of my super pack, but I don't know if you can buy it. I don't think it's for sale anymore. But unfortunately, I stopped. I wanted to do the whole concurrent package, but because there wasn't enough demand, I never continued. What I'm saying is that CopyOnWriteArraySet and ArrayList are more complex than you might imagine. And part of that complexity comes that they've got some very strange way of writing loops. And you need to sort of follow around a bit to try and find out why they're doing the loops like that. But also, they always try to avoid locking if they don't need to lock. So there's a very big emphasis on not locking. CopyOnWriteArrayList does have some issues. For example, if I do this, let's try and make a large CopyOnWriteArrayList. InStream.range, 0 to 10 million, and I want to make a large. What is this important? So boxed dot parallel. I'm going to do parallel to make it faster. Dot to collection, and here I'm going to use CopyOnWriteArrayList : new. Do it in parallel so they can do it faster. Okay, it's like that. To collect. Collection. This gives me a list of 10 million items. Okay, do it in parallel to do it faster. And let's do the time around that to see how quickly I can create a CopyOnWriteArrayList of 10 million items. Now the problem is every time that I change a CopyOnWriteArrayList and add one element, it needs to make a copy of the previous array. and it makes new array, copies old one in there, and so 10 million is just too slow. Let's try 10,000. See how slow that is. My guess is going to be half a second. It seems to be like the standard number we get here. So let's see if that's correct. It's like the standard number for quadratic cost. It's like half a second. Okay, it's a bit faster. That's not brilliant. So if I make it, let's start with 50,000. Okay, if I double it to 10,000, to 100,000, so I got some 88 milliseconds too. Okay, doubles the size. That's not too bad actually. Just wondering about this. 200,000. 600 milliseconds. 400,000. Oh. All of a sudden we got to the stage where doubling the size quadruples the time. So 800,000 is probably going to take a few seconds to complete. Right. So if you need to make a large list like this, my recommendation is to do this slightly differently. Is to start by saying is to make an array list, then pop that into a CopyOnWriteArrayList instead. So in other words, you're going to do something like this. You're going to say, make this into an array list. We'll just say toList, which will be very fast. And then you create a CopyOnWriteArrayList from that. So a new CopyOnWriteArrayList of this array list. Because it's an array list, there's even an optimization for that within the CopyOnWriteArrayList to just take the array and copy it over. We're done. So that's a lot faster. It's 192 milliseconds as opposed to over 5 seconds. So that's anything. Constructing it and changing it is expensive. It's quadratic. If you want to construct a large one of these things. But iteration safe, so that's good. LinkedList only has one benefit, and that is no, it doesn't even have one benefit. There's no benefit. And famously, somebody asked about LinkedList, and the author of LinkedList said, LinkedList, ? Never use it. So even the person who wrote it refuses to use LinkedList. And the reason is that LinkedList has, unfortunately, first of all, it uses a lot of memory, but also, unless you're accessing elements at the beginning or the end, it's not going to be very fast. So if you access, say what you remove the elements in the middle, you first have to move to the middle in order to remove the element. So it's not a good collection. Rather than use it, if you need to have a FIFO queue that's not thread safe, rather use ArrayDeque. All right. So we've done the lists. I think we're done with that. We also have. There's one more thing I want to show you, which is the sequence collections. But I'll do that once we've done sorting. So we can sort elements by specifying a comparator. And nowadays we can have simply a list of string list equals new array list. We say collections dot add all list comma G H, that's supposed to be H I A C Z, and we used to have to say collections dot sort of the list, But nowadays, the sort on the list actually delegates through to list.sort. So list.sort over here. And there are three methods on collections like that. There's collections.sort, there's collections.reverse, and there's collections.shuffle. Right? These three. And they each have an operation on the list. They moved the sort method directly onto lists in Java 8. So we can say list.sort. We have to pass in a comparator. We're going to just pass a null, which is that then they're going to use the default comparator. Reverse, this is now Java 8. Reverse, they've done in Java 21 or 20, I think it is. So we can say list.reverse, reversed, and that returns a new list that's been reversed. It doesn't change the original list. It gives you back a new list. And it's a view on the original list. So this reverse method would actually reverse whatever you've got. It would change what you're looking at, but reverse does not change it. It just returns it in the opposite order. So for example, if I print out the list here, that's before sort, after sort, all over here. So I'm printing it out. You'll notice that it doesn't change in between when I call list.reversed. The list doesn't change. Oh, wait. So initially it's this value, then it's sorted. Then even if I call reversed, it doesn't change anything. But if I call reversed, it's going to reverse the list. And as I said, reverse doesn't change it. It simply creates a new list, which is reversed. So let's print that out as well. It's reversed. You see, after I've reversed it, the original list stays the same, but reversed is then simply the opposite of that. It's just a view on your existing list. All right. And of course, we can have different comparators. So if I've got a class in here that I'm using, I can make a comparator comparing, the individual elements. So let's make a record over here. Let's make a record student with the string name int IQ. And if I want to make a comparator for that, I can say comparator of student would be comparator dot comparing. We'd start with the name, for example. So it's going to be student current name. That's a string. And after we want to compare the int, then comparing int, and it's going to be student current IQ. And that will then compare these. All right. Good. And that's basically what this does. It's the extractor functions. The other thing is with sorting, we've done already a sorting performance of LinkedList and ArrayList, but I haven't shown is the parallel sorting of ArrayList. That's not supported by default. So let's go and copy the code from before. Not this one, it was this one. No, I wanted to make this one. Okay, that's what I wanted to have. We're going to copy this code down to the parallel sorting performance. We want to show you something here. So we had 4 different collections. We had the int array, integer array, if you remember that. We had the linked list and the array list. And what we want to do is to sort them, each of them, and parallel sort them, and to see what the difference is in performance. So how are we going to do this? Right, so what we'll do is we will try to think of a good way to write this. So it doesn't become, I don't make the same mistakes as before. Okay, so this over here is just doing a sort. Array sort. And what I want to do is I want to sort it. I want to sort a clone of the elements. In other words, I'm going to say test sort of. Okay, so I need 3 different sort methods. Taking the numbers 1. That'll be the first one. It's going to basically do this over here. Test sort numbers 1, create method. One take an int array of numbers. Okay. And so what we're going to do is we're going to make a clone of that. We're going to say var clone equals numbers dot clone. Oh, switch to Greek. That's not good. We're going to make a clone of it. Then we're going to change it to them. Okay. And we're going to sort it. We're going to sort the clone. All right. Then we're going to make another clone of it. And we're going to do the time again, but this time we're going to do parallel sort. That's going to be the parallel time. Okay. So the type of class here is going to be printout numbers.get class.get type name. We're going to print out the type name, we're going to print out the time over here, and the parallel time. That's for an int array. We're going to do the same thing for an integer array. Unfortunately, they're not related, so you need to have separate methods for it. Integer, they'll all be exactly the same. And we're going to do the same thing for a list, except it won't really work. Because for a list of integer, we don't have the option of a parallel sort. And also, we need to make an instance of that. So a clone of it, how do you make a clone? Well, we could make an instance of the object, make a copy of it. The clone method is available. It just isn't there because it's. So what I'll do is I'll skip the linked list. I'll just do an array list instead, so we can use that directly. Let's delete the linked list. So we're going to have 3 things. We're going to have an array, an int array, an integer array, and a list of numbers. Like that. There's 3. So 3 different ones. So and we can make an array list, which means we can simply make a copy of it. Array list. To collection. Array. This kind of code. All right, so we've got 1 to 3 numbers, and down here we've got the test sort with an array list. We can make a clone of it that gives me back a list of integer, which I have to do typecast to, and then I can simply say list.sort sort of null for the sorting. Close sort. I can't do the, unfortunately, I can't do the parallel sort because that's not, doesn't exist. But I will create it in a moment. So that's going to happen in a short bit. There we go. This is now a nice little demo. You're going to see the single sorted time, the parallel time for each of these. So test sort numbers 1, numbers 2, and numbers 3. Let's run the code and we'll see how the single-threaded one compares to the parallel one. This with 1 million elements. You can see that the int array is a little bit faster. But once it's warmed up, we're getting very nice speed up. So we're going from 200 milliseconds down to 35 milliseconds for the parallel version. That's quite a big difference. Even the integer is from, okay, that's a little bit, not a big difference, not as big a difference. Probably what you want to do is to do a little bit of a GC and a sleep in between each test. So once I'm done, system.gc, thread.sleep, just to give it a chance to recuperate from all those objects that's been allocating. And then we should see slightly better results, slightly more consistent results. It still doesn't make a big difference. It seems like the parallel sort. We're doing the sort of the parallel sort on the. So I'm doing parallel sort on the integer array, but it doesn't seem to make a very big difference. It's here it's bigger difference. It's more than twice as fast. Whereas with the int array, it's a much bigger difference. But it is a different sorting algorithm. And I don't have that option with the ArrayList because ArrayList doesn't have a parallel sort. So what I can do is I can do the following. Go to list.sort. I can copy and paste this into my code. And I can make my own parallel sort method. So this is how the default method looks. And I can say over here, private static void sort, taking private static E, taking a comparator and a list of E. That's a list, comma, comparator, super E. Instead of saying this, I'm going to say list.toArray, list.listIterator, and then we can say, instead of saying sort, we can say arrays.parallel sort and run that. Oh, and then also what I want to do is to uncomment that so it becomes available. We're going to do our own parallel sort method. It's going to be clone comma null. Okay, it's complaining about the comparator, I think. Comma comparator of integer. Oh, it's calling the wrong thing. I think it's imported it's done a static import on the parallel sort, which I didn't want to do. There you go. Let's delete that. It's going to be arrays. That's going to be that's the parallel. That's arrays dot parallel sort. Yeah, I think I've got the name wrong as well. And arrays dot parallel sort. And it's called, oh, it's supposed to be called, oh, okay, this is where the mistake came. It's supposed to be called parallel sort. Okay? I'm just checking if you're awake. That's the thing. Just checking if you're awake or not. Paying attention. So integer array, big difference performance. But now you can see that the ArrayList is also not too bad, actually. That's quite a good difference, quite a big difference, actually. It's like 4 times faster. And you might wonder, well, why don't we always do it this way? why do we do parallel sorts? Why did we have parallel sort? Well, there you go. Good question. You can write it yourself quite easily, just like that. And it doesn't always help you because, for example, if the list is sorted already, parallel sort will typically make it slower. So just keep that in mind. All right, I'm going to check this in. This is demos halfway point. And I'm going to push it. This isn't going into the carbots branch. So if you, the original one, the master is just the outline. And we'll take a break here because we all need a break, I think. I certainly need a break. When I start making mistakes like that, I know I need a break. So let's take a break and we'll continue in 7 minutes' time. Test, test. There we go, that should work. I'm not sure why that microphone just stopped working. Maybe it's tired of me speaking. Spent many hours yesterday doing a recording for you, and now it seems to be working. It's a different microphone, different setup, but as long as it works, and it should be clear enough, I think we're good to go. It's annoying. I like the microphone. And the cables branch, but just one other thing missing. Yeah, there's a chip on this chip. Just find it. This chip. This is the chip. It's going to take a while to get this fixed. This is just here. Joys of technology. But as you saw, when everybody had a problem, it was my fault. It wasn't your fault. It had to be, but it's got to be. It's like everybody then know that it's me. All right. Thanks for your warnings and telling me about this. And let's continue. Cobbles branch. Good. All right, where are we? We're worried about parallel sorting. Don't worry about that. You're not going to do it very often, hopefully. Do it all the time, and you got a bigger problem. All right. So we want to look at sets. Sets are basically like mathematical sets. You can do unions with add all. You can do dissections with retain all, or stream or filter. And we've got several different ones. For example, the TreeSet. The TreeSet sorts it in the natural order, or you can pass in a comparator. If you pass in a comparator, then it will retain that comparator. We use that comparator in future to do the sorting. Now, it's a red-black tree, and what that means is the following. Let's say I've got a set over here of integers, and I'm going to put 1,000,000 integers into that set. So it's in my set over here equals new TreeSet. And I'm going to go 0 to 1,000,000. I'm going to add into the set of add I over here. So it's the elements are added in the correct order from 0 to 1,000,000. If I just had a very naive tree implementation, I would have something that looks like this. You'd have your noughts, and then to the right of that, you'd have 1, and then to the right of that, you'd have 2, and then to the right of that, you'd have 3, etc. So it would be very, very inefficient to look for anything. You'd have to basically go and iterate through all the elements to find your particular element. What they do instead is, as you add them, they balance them using red-black trees. I'm not going to explain the details of it, but as far as I know, the red-black tree is guaranteed to never have a bigger depth than 2 times log 2n. So in other words, if I've got 1,000,000 elements inside here, it's going to rebalance it for you, and you're never going to have more than 40 layers inside that tree. That's sort of, I think it's a guarantee. And the number 40 comes from log of 1,000,000 comes out as 20, and 2 times that is 40. So that's the maximum number of layers. So if I'm doing a lookup, it's going to be a maximum of 40 lookups to find my element inside the tree. If you want to see how to verify that, you take the TreeSet. The TreeSet is actually a TreeMap, contains a TreeMap. And the TreeMap has got a bunch of entries. Each entry is a map entry, and the map entry has got a parent in it. So what you can do is you can simply count how many parents does each entry have, and by counting that, you can figure out precisely what the maximum depth, what the average depth is within that tree. it's quite easy to find this information. And you can do it simply by iterating over the entries and then looking at the parents. So if I change this to be a map of integer, comma, integer, for example, let's call it a map instead of a set, a tree map here, and then I go and I say map.put, map.put. It's going to be I, comma I, and then I iterate through that, and I'm going to go so iterate through it with the through the entry set. Each of the entries is going to make this a bar. Print out entry.getClass. You see, this is this inner class inside the map that has a parent inside. Of course, if parent is null, then you're looking at the root node. All the other ones will have a parent. It's only the root within the tree that will not have a parent. Everything else will have a parent. So running that should show you that they all are TreeMap entries, the ones that we looked at as well. And then all you need to do is it finished? Stop. Look at it printed out. We're going to count. So we're going to say depth int depth equals measure depth of entry. Okay. Measure depth is quite simply this. We're going to have here my entry. We're going to find the field parent. Parent equals entry.getClass.getDeclared field parent. Okay. And I'm actually going to store this as a field. It's going to start as being a private static field parent. And we're going to say if parent is null, then we can initialize it. First time we're going to initialize it. Of course, this could throw an exception. We're going to manage the exceptions internally. We're not going to propagate them here. So it's going to just be catch reflective operation exception, and that's going to throw illegal state exception, illegal state exception of E. So if the parent is null, we initialize it. We load the declared field parent, and we're simply going to say int depth is at least one, which is our current one, while parent.get entry is not equal to null entry. Garbage collect. If you can find anybody who can actually tune the garbage collector, that'd be nice. You're going to say entry equals parent.get entry. Do cast. Right? So we simply roll up the hierarchy and then we return depth. So the smallest step should be 1, the biggest should be no bigger than 40. Very simple, and what we'll do is we'll put this into a list of integer depths equals new ArrayList. In fact, what we can do is we can do this even better. We can say map.entrySet.stream.map to int, and we can say _4_2 TreeSet current measure depth. Then we're going to say the summaries, just get those out, print them. All right, so that should print out the depth average, the maximum, the minimum, etc. So very easy to do. I'll have to open up the module for myself to be able to do this. /40. That was the maximum depth, because I'm going to say here I'll just say a maximum depth equals 40. Okay. So I need to open this up because it's, of course, now heavily protected. So we need to see. I'm not running inside a module, so I can simply say here add opens, minus minus, add opens, Java base, java.util equals all unnamed, because we're inside the unnamed module, and now hopefully this will. Now, also must make it accessible. So the first time when I make the parent, I need to also make it accessible. What about that? Parent accessible. Sure. So it's chugging through all the million elements. You can see that it didn't work. Why didn't it work? I don't know. I thought it should have worked. Why can parent never be? Oh yeah, I forgot to say depth plus plus. Why didn't you tell me that? I was expecting KP to say, hey, if you forgot about, well, you won at least. To say, hey, you forgot. If it's the depth plus plus, you're counting how many depths, how deep. Hopefully this will work. All right. So we can see that the maximum depth is 37, just under 40, like I said. The min is 1. As I said, that's the root object. And what we can do is we can do this. We can say if we can say if depth is 1, depth is 1, we can print out the entry. So just for interest sake, because that's going to be the root. That's going to be snap pang in the middle of my tree. It's a binary tree, so we've got two sides going down. The one in the middle you'd expect to be around about 500,000. What is it? 5 million or 1 million? It's 1 million, so 500,000 roughly, but it's not. You see, it's actually 260,000. So it is slightly slanted in one direction. That is the problem we have with these subset trees. But we see the min is 1, the average is 19, and the max is 37, which is not too bad. So from average, you're going to have about 20 lookups to find your element. And the maximum is going to be 37 lookups to find your element. Right? That's your red-black tree. And you'll see this one is going to be used for other cases as well, not only for the tree. You'll see this happening in a moment. Now, if it was a perfectly balanced tree, you would have never more than 20 elements to look for. There's also a concurrent skip list set. Now, the problem with the normal tree set is that it's not thread safe. So if you say int stream.range 0 to 1 million and say .parallel for each, set and add, the set has to be a local variable. It's going to be a set of integer. If I make this into a tree set equals new tree set, that's going to fail horribly. And if I print out set.size after this, several things can happen. One thing that can happen is you might end up with the incorrect answer, which is at least, that's one thing. You can have an all point exception, you can have a concurrent verification exception, and you can even have an infinite loop. It's on the right code. In our case, the size is completely wrong. It's supposed to be 1,000,000, comes out of 678,000. And that's what the size variable says. If you actually go and count the elements, so I'm iterating through the set, I'm going to say size plus plus, this is just a local variable, equals 0. Then I print out that size. In fact, let's call that count rather than size. So now it's picking the wrong ones. Okay. Oops. This time we got an exception, null pointer exception. I told you it's unpredictable what you might get. It's anything, not anything, but there are lots of different things that could go wrong. Now I'm counting the size, and it appears like I've managed to get an infinite loop inside the tree. So at some point, parent points back to itself or something like that. Inside a loop, there's some loop where it points back to itself. So it never, or maybe one of the left or right points back to itself. So that also doesn't work. So if it gets rebalanced whilst it's busy being modified, you're going to have some very weird results here. Okay, so that doesn't work. We were not having any joy here calculating this. But if you take a concurrent skip list set, then that does work. So if I change this to concurrent skip list set, then it's TreeSet. Now the concurrent skip list set is not used that much. It's a fairly complex piece of machinery, and it's not used in that many different settings. So we do have to be careful because that always is the likelihood of error inside. I need to just change this to, I thought I was on Java 21, but I'm actually running JDK 22, so we'll just stick with 21. All right, so this time it's both are exactly minutes, so that's what you want. There's CopyOnWriteArraySet. This one is quite nice for very small sets. The moment you go past a certain size, it's not going to be that efficient anymore. So, 3 or 4 entries, 3 or 4 items, it's okay. The problem is that you actually can't construct a very large array set, CopyOnWriteArraySet, because it just takes too long. And inside there's actually a CopyOnWriteArrayList. Every time you add an element, it checks whether it's there ready. And if it's not there, it adds it. But this is a very slow process. So, I'm going to say use with caution. You might use it, for example, for a listener. You're not going to, most of the time, you're not going to have thousands of listeners. You're going to have just 1 or 2 listeners. Not going to have that many. So that might be a use case where you might be able to use that. Okay, we get to another topic which I sort of touched on very briefly, but not that much, which is hashing. And the idea is the following, that what we do is want to be able to find elements again, find objects again. So we invent a number that is associated with that object and use that to discover the object at a later stage. And this is a very common approach we use for finding objects in all languages, really. Now, let's say, for example, I've got an array of 10 elements. That's my array. So it's an object array of 10. And I've got some object, and it has a hash code of 32. Well, 32 doesn't fit into object of size 10. So what we do is we can take the number 32, we can say 32 percentage 10, take the remainder, and that gives you the answer 2. Okay. So that thing gets morphed to 2, and then we get the position 2 inside the object array to start looking. So that's one way we could do the hashing. Of course, what can happen is that 2 objects have the same hash code. These are 2 different objects, but they have the same hash code. So if you end up in the same bucket. You can also have a hash code that's completely different. 512 and 512 percentage 10, again, it ends up in the same bucket. Okay. Now, percentage remainder. Remainder is a rather slow method to call. It's the slowest CPU instruction. So ideally, we want to use a different mechanism for finding your position inside the array. And we also have to have a technique for managing clashes. So basically, what we can do is, one way to do this is that if, for example, we find that the position is occupied, we just take the next position. Now, that's not a very good approach. Another way is to say we're going to have a node, and the node points to the object, and if the object is there already, we also use .equals to check whether it's the same object. Right, but both of those techniques give you performance where you might have lots of clashes on the object, and you might end up with having to navigate a long chain of elements in order to find your object. So let me show you an example of how this could happen in Java 7. So if you go back a few years to long time ago, integer, okay, let's do I'm going to make a special class here called a pixel. I'm going to make an inner class called pixel, and for now it's going to be just a class, it won't be a record. It's going to have int private final int x comma y constructor and the hash code and equals. So I'm just going to do the default. Not going to do anything special here, just the normal default hash code and equals as IntelliJ would normally generate. So it's going to be we're going to make a hash set of pixels equals new hash set, and I'm going to start with a really bad hash code that's always going to clash. Return 42. So almost all the pixels are going to go to the same bucket. Okay. Now, if I make a list of pixels, we'll start with a list of pixels. List equals new array list. That's going to be very easy to construct. We go and make 100. Let's call this x 100, and y up to 100. So it's 100 by 100. It's not that many. It's just 10,000 items. And we're going to say list.add new pixel x comma y. Okay. And if I then say pixels.add all list, we're going to see that it's going to be quite slow to run this. So we're going to run that from Java 7. Java C. Package here. Oh, package. That needs to be Java 7. So Java C, all of this jazz. You need slashes there. Slash. Java C, /5, and _5, 1. And then we're going to run it also in Java 7. You'll see it's not that fast to construct this. And if I double the size, or if I add an element, if I add a new pixel, measure that as well. Well, adding one probably won't be, we won't notice one. But if we double the size of x to 200, for example, and recompile it and rerun it, it gets a lot slower. I've just doubled the size and it's become more than 4 times as slow. If I double the size again to 8,000, Java C, and run it, it's going to probably be like 10 seconds or something. Okay, 7 seconds. It's again. So it's quadratic, the cost, because everything is sitting in a single item. To add one element is linear, but to doing that n times, so it's n times n, we get to quadratic performance. All right. If I run the exact same code with Java 21, watch what happens. Okay, it's not much better. We've got the same problem. So 7.7 seconds in Java 7, in Java 21. Have we made any progress since then? It actually looks slower than before, which is kind of disappointing. You'd think that things would improve, but no, it doesn't improve. In fact, it looks worse. I'll let this run and we'll see how long it takes eventually, whilst we continue. Hide that away. Okay, so this is the situation at the moment. And first of all, the percentage is not how it's actually done. It's actually using bit masking, which means it's never going to have a size 10. It's always going to have a size power of 2. So let's say size 16 over here. And it's going to say ampersand 16, sorry, 15, instead of saying, and there you're actually going to end up having 0. If it's 32, it's 0. They're all 0. All of these are 0. So that's kind of disappointing. And so what they do is they actually shift the bits around a bit in order to get better distribution inside the HashMap. And the bit shifting was fairly complex in the past and took a few CPU cycles. So what they did was they simplified it. Oh, look at that. It went from 7.7 seconds to 36 seconds. That's pretty bad, isn't it? It's like, wow, I didn't know it was that bad. Right. That's Java 21. And that change happened in Java 8, actually, because they changed things at that point. So going back to Pixel, it's a real problem when you've got multiple objects with the same hash code ending up in the same bucket. If they're different hash codes, it can sort of cope with that if they end up in the same bucket. But if it's the same hash code but different objects, it really struggles. So what we can do there is to go to the pixel and make it comparable. If we say implements comparable of pixel, then and add the compare to method in there. I'll leave the hash code as it is. And I'm going to compare x and y. So we're going to say if int results equals integer dot compare x comma o dot x. If result is not equal to 0, return result. Return integer dot compare y comma o dot y. And this way we can actually optimize inline this and inline this, and then we can There are ways to optimize this, but I'll leave it like it is. Okay. So what I'm going to do is I'm going to run the code again, recompile it, Java 7, recompile it and rerun it in Java 7. You'll see Java 7 won't make any difference. It'll be same, roughly the same speed, 7 point something seconds to run this code. But if you run the code with Java 21, it should be a big, big difference. Well, look at that. So we've gone from 36 seconds down to 200 milliseconds. That's a massive improvement. And we get that because of the comparable. This comparable is your safety net. This is the safety net you want to use. If you ever make a compound object as a key, you always want to use comparable. Yeah, that is wild, isn't it? And they built that into the language. And my recommendation is whenever you have a compound key in a hash map, that you make it comparable, because it's impossible to know that your hash code is perfect or really good hash code. And this way, at least if you make a mistake with your hash code and it's not that great, you can at least get good performance out of your hash head. Of course, if you have a better hash code, that's better. But this is quite amazing, isn't it? All right, so, and this only applies if it is a comparable object, otherwise this won't work. All right, what else can we do? So the first tip is that your hash code should be as perfect as possible, which means that if you have different objects, they should have a different hash code, if possible. You can't always enforce that, but if you can, that's what you want to try and do. The second thing is that you want to have a compared to as a safety net in case you get it wrong. Now, let's go back to this generated hash code. And we're going to try Java 7 again. You're going to run it. And you're going to try how well that goes. This is now, oh, that's pretty good, 77 milliseconds. Java 21. And we get 43 milliseconds. That's also pretty good. Now, because we've made it quite a bit faster, let's also increase this a bit. Let's make it a bigger monitor, 1920 by 1080. So we've got a bit more work to do. And we'll do the following. What we'll do is we'll do a pilot. Java 7. It's going to take a bit longer, 1 second. And Java 21 is a little bit slower, a bit on the slower side. Now, at the moment, this is not a very well. First of all, the experiment is not that good because we should give it a name for add all, give it a name here. We should call this several times, not just once. So let's do this. And we also should look up, should say, pixels.contains all, list.contains all, I think it's that way around, list.contains all pixels. And measure that as well. So it's going to be lookup time and add up time. So I might have got the wrong way around. I think that's right. So list contains all pixels, but it might be the other way around that we should do it to make it good performance. No, it's wrong. Test. Test. If it doesn't complete quickly, then I've got it the wrong way around. Let's swap this around. I can never remember which way around the correct one is. As you saw, I got it wrong. Because one is a set comparing the items to what's in the other one. That was the other way around. Okay, so that's it. So that's lookup time. And what we'll do is we'll run that 3 times just to get it to perform it a little bit. Ideally, you want to do this a bit longer, but just, 1 to 3. Okay. So let's run it 3 times to test add all and contain them. And once it's warmed up a bit, we get to like the second, roughly a second for add all, and a bit more than half a second for lookup time. Now, if we go back to Java 7, are we on Java 7? Java 7, compile it, run it. We see similar results, although the add all is a little bit faster than Java 21. But we do have a lot of clashes, right? And we do have a lot of pixels with the same hash code. And you can verify that by going through and taking our pixels and seeing how many of them are actually distinct. So if you do this, if you say, for example, list.stream.map to int object colon hash code, it's going to generate the hash code for each item, and distinct var. That will show you how many, wait, count. Show me how, show how many distinct hash codes we've got. Ideally, distinct should equal the size of the list, okay? But it's a far cry from. If you look at distinct, it's a much smaller number than list.size. 60,000 distinct hash codes, 2 million items. So there's a clash of like 30 to 1. Yeah? So let's go to a pixel, and instead of having this hash code, we're going to change it to say, return X left shift 16 bits, X or Y. Now I've got always different hash codes, no more clashes. Compare to should actually never be called, because there shouldn't be any clashes. If you run the code now, in fact, let's run it. Let's run it first of all in here. Java 7, let's compile it. Java 7, compile. Oh, of course, we don't have streams. So that's not going to work. I'll just comment that out. I don't want to keep that in there. I can do it a bit differently. I can have a here set of integer hash codes equals to HashSet. We'd say hash codes dot add pixel. This is going to just be a pixel. That. And then we're going to just, let me just say that distinct equals, we can say hash codes, let's print out hash codes. That will give us the size of the distinct hash codes versus the distinct. All right. Now it should compile with Java 7. And should hopefully run Java 7 as well. And it should be good performance actually in Java 7. So the add, once it's finished everything. Oh, that's good. Must have made a mistake. Let's look at the pixel again. Oh, X for X. See, I need a break. We all need a break. I would have expected at least KP to spot that one, but no. Fast asleep at the wheel. All right, so try that. Java run, and now look at the performance. We've gone down to like 100 milliseconds for lookup time. And add all is 160 milliseconds. That's really great, really nice. And if you go to Java 21 and run the same code, it is a lot slower. It's 3 times slower, 4 times slower, 6 times slower than that. That's a big difference. And the reason why this is such a big difference is that it's called overconfidence, right? Overconfidence. Because they know that they've got this compare to, which actually I don't think is called. Let's see. If true, throw new assertion error. I don't think this is ever called. Java 7, try that out. Because we don't have any clashes, right? At least no clashes in the hash code. So maybe it's called, but I'm not. Let's Java 7 for sure it's not called. Java 21 it might be called, although I don't think it is. Let's see. That's not called. It would be called if you had lots of objects with the same hash code. But if they're different hash codes, then it doesn't need to do the compare to. Okay? So this proves it's not actually being called. Now the problem with the hash code is that it's overconfidence on the side of the people writing HashMap. A better approach is to return a number that's the smallest number that is also distinct. So if I say x times, for example, 180 plus y, it's going to be always distinct, and it's going to also be a perfect, so a perfect hash code, and it's going to be the smallest possible. So that's what you're looking for. Small numbers so that all the lower bits are set, and it should work fine in Java 7. So it should be even better than the previous one. In Java 21, it should also work really well. Okay, so we get good performance there as well. And that's what we want to get to. So it actually is worthwhile to spend a little bit of time on the hash code. And this is also true if I make a record out of this. So if I make a record in Java 16, the equals you don't need, that is the default one. But you see what Intelli did? They very nastily stripped out my lovely hash code function. That's what I call a bug. That's a bug. So what I've done is they've stripped it out, and now we're going to have clashes. And they shouldn't have done that. So, let's add the hash code back again. Return x times 1080 plus 1. So you find the same problem. So if I don't have this hash code, look at what the performance was before. 63 milliseconds and 100 milliseconds for add-on and contains. So I'm going to compile this with Java 21 because Java 7 doesn't have records. Can you believe it? In fact, we'll just run it. Java, let's delete the class files. Oh, okay, that doesn't work. So Java, okay, so let me just compile it. We run it, and you should see with the normal record, it's actually like really bad performance. And then you put in the magical hash code and recompile it, and we get much better performance. Like more than 10 times faster. Amazing, isn't it? I don't think it's, I mean, I've not heard anybody say, except for me, I'm the only one who've only heard myself say, and I've been saying it since I first heard that they were going to do records. I've been saying that if you make a record, you want to say if at least implements are comparable. At least that. In case you have a lot of clashes, you can at least optimize that a bit. But then also try and add your own hash code that's a bit better if you use it as a key. But if you don't use it as a key, you don't need any of it. It's only for that case. And if you have a lot of these things. All right, we need a break. I said we need a break. I've done almost everything. Just one more thing. If you want to make a concurrent set, you can simply say ConcurrentHashMap.newKeySet. That gives you a set. Should just be a set over here. Set of, for example, integer. So if you want to have a thread safe set, the class, you just say ConcurrentHashMap.newKeySet. There wasn't another way of doing it before, which you don't really need anymore, which you can say collections.new set from map, new concurrent hash map. It also worked, but nowadays you just say the first one, which is concurrent hash map. Use this one, new key set. All right, let's take a break. We've got 1 more hour left. So if you have any questions, bring them after the break. We'll give you a slightly longer break because we've been going for quite a long time. And see you in 10 minutes. All right. Comments, questions? No, it doesn't look like it. All right, so we've done hashing, which I think went well. Good questions there. And I mentioned maps already. Maps are basically one-to-one dictionary between keys and values. And the most common one, I think, is HashMap. The problem we have with HashMap is that it's very sensitive to, first of all, these clashes, which we saw already. And I've actually written a map clash inspector for that very purpose. Map clash inspector. We need to send you that link as well. Stick that here. Map clash inspector. So this gets you a little newsletter that shows you how to actually measure the number of clashes you have through hash code. It does some deep introspection, deep reflection on the map to see whether or not or how many clashes you have. They also have within strings this idea for cached hash code. Now that's quite interesting. The string is one of the few classes where you actually have a hash code that is linear. So the cost of calculating the hash code is linear to the size of your string. So if you have a very large string, it takes longer to generate the hash code. And in order to improve that, they've got the cached hash code. Just remember, clip this form down here. This is why I was using my other microphone, which doesn't have the problem. All right, so we've got over here our hash, which defaults to 0. That's cached inside. They also have a boolean to see whether or not it has been set ready. No, sorry, it's true if the hash result is 0. Now, we don't normally need to cache a hash code. In fact, I've never done it. I've never needed it. It's never been of any benefit to cache the hash code. Because if you, for example, have strings, the strings have got a cached hash code anyway. So there's no reason for us to cache it as well. I want to show you one more thing, which is going to upset KP. KP is going to say, why on earth would you do that? So we've got a hash code over here, the pixel, and just one little thing. I'm going to run this. This is not Java 21. I'm going to compile that and run it, make sure that it runs properly. And you see it's quite fast. It's about 50 milliseconds or so for the lookup, 80, 90 milliseconds for the lookup, and about 100 milliseconds for the add. So it's fairly good. Now, what I'm going to do is I'm going to change the hash code to the following: return plus x plus the minus plus y. I'm going to create a string, then going to say dot hash code on it. Right? Let's see what happens now. I'm going to compile it. Remember, our best time for add all was 100, and lookup was 80. Run it again. And it's actually not that bad. It's not great, but it's not that bad. The distribution is quite good. Like, if you look at the number of the distinct hash codes, it's almost completely distinct. that's quite good. And the lookup time is also quite good. But I'm making a string every time and then calling hash code on that. And the funny thing is, so the performance is like 260 milliseconds in the worst case, for the lookup time in best case, 380 milliseconds for the add-all. But if I take out the hash code, in fact, if I go to just the default, which is to say pixel int xy, without any other fancy things in here. So I'm going to comment out the rest of the pixel, like that. Actually, I can leave the compare to in there. It's not going to be called anyway because it's not. This doesn't say override. So this is just a plain pixel with nothing else in it. And if I compile that and run it, even though I'm constructing a string in the other case, it's much, much worse. So it's actually better to just create a string and throw it away than to have a bad hash code, default hash code. Isn't that interesting? So let's put the hash code back with the string without the comparable. And performance goes back to pretty good. Or we have a better approach, which is the actual minimum hash code. Then you end up with the really great performance. If you do a lot of hashing, this can make, of course, a big difference with performance. All right. All right, so let's continue. The HashMap, the problem with HashMap is, first of all, the clashes. As I said, I've got an inspector that allows you to test how many clashes you've got, if you have a lot of clashes or not. But secondly, we also have another problem, that is that you can easily get infinite loops inside your HashMap if you have multiple threads using it at the same time. So we want to be careful of that. We don't want to have too many, we don't have any multiple threads using it. In fact, the only time you want to use HashMap is if you're using it only within a single method. The moment you're using it within multiple methods or within multiple, or as a field, you want to rather use something else. Oh. I couldn't figure out why my mouse wasn't working, but I had my phone lying partially on my touchpad, and it wouldn't allow my mouse to move. Very nice. All right. So let's make some other things, which is the computer absence. If you want to make a map of numbers, for example, you want to have a map integer comma long, where this is the squares equals new hash map. And what I can do is I can calculate that. I can calculate it using computer absence. So I can make a function here, a function for the squares, and the function is going to be used for calculating the long based on the integer. So I can say squares dot computer absent, I comma the key, and then I've got the mapping function, which basically casts the key to long key and multiplies it with key. So it gives me a bigger range. And this over here, we can put into a constant. That's a function. That's a square function. We can write it like that. So we've got private static final function over here, key and cast key to long and multiplied by key. So this is quite nice because we've got computer absent. Somebody asks for something, we can just put it in there. hash code should likely be non-abelian times and plus commute, which will lead to more collisions. Well, ideally, you don't want any collisions. You want to have, I'm not sure what non-abelian is. I'll have to go to ChatGPT to discover non-abelian. But times, the problem that you have is when you do shifting exactly 16 bits. That's a very bad hash code. That's a really, really bad one. So you don't want to do exactly 16 bits. If you're going to do shifting, you can do shifting in XOR to move bits around. That's fine. But you want to, right, okay, so it's associative. But what I'm saying is that if you shift the bits around, make sure you don't shift them by exactly 16, because of the rehashing within the hash map, you end up with a very bad distribution. You end up with lots of, not collisions, but you have bucket collisions, not hash code collisions, not bucket collisions. Lots of elements in the same bucket, but with different hash codes. All right, so if you want to generate a bunch of numbers, you can do it that way. Compute of absent will generate them. There was actually a bug when compute of absent in Java, when was it? Java 8, I think it's Java 8. I hope you're not using Java 8. If you are, change immediately to Java 11 or Java 17 rather. But in Java 8, there was a bug. There were two bugs in compute of absent. The first one was that it wasn't consistent with behavior. You're not supposed to change the structure of the map from inside your function. If you do, random things can happen. And they actually throw an exception in Java, from Java 9 onwards, if you try and do that. You get different types of exceptions. One is a concurrent verification exception. Other one, I think, is an EnumSet exception. But they don't allow you to try and change the map from inside the function. The other problem that we had in Java 8 was the compute of absent had a lot of contention when you didn't have very many different possible values. Then you had really bad performance. And there were workarounds for that, which I'm not going to show you because I don't think it's necessary anymore. But these have been fixed. So if you were using a more modern version of Java, that'll be gone. Now, concurrent hash map is really the way that we should be using. It's really the map we should be using rather than hash map, because it's always thread safe. It's weakly consistent iteration, and it allows us to the concurrent hash map allows us to have multiple threads using it without a problem. So I'll tell you a story about KP and me. This happened a long time ago. I think I know who KP is. Came with a big thread with big heap dump, which you couldn't figure out. Massive, a very, very large heap, out of memory error, and didn't make any sense because there was enough memory. And we looked at it, and I looked at the file in like VI or Notepad or something, and I could see that file was serialized output. Just had this pattern. And we actually wrote some code to investigate it. And what it was a hash map that had been serialized. And what can happen is if you take a hash map, normal hash map, and nothing special, integer, comma, long, map equals new hash map. And you go and you have multiple threads that are writing into the map. And one thread writes whilst the other thread is busy resizing it. Then you can get an infinite loop inside your hash map. So let's see if this can happen. We're going to go and do an int stream over here. Let's try with 10,000 numbers. It should be enough. Dot parallel dot for each I map dot put I comma So we've put the values in, and after we print out the size, the map size, which will not be 10,000, will be something else. And maybe this will cause an infinite loop inside the map, perhaps. Okay, it didn't. We got lucky, but it could. Now, the number's not 10,000, so you see there's something wrong. And maybe there is an infinite loop in there. If we iterate through it, through here, we might actually end up with seeing an infinite. We're going to do a counter here, into count equals naught, count plus plus, and if an infinite loop is inside there, this will never return. So print out the count. Let's run it again. I'll probably have to increase the number of elements. Let's make it 1,000,000. Just to increase the probability that we're going to see the race condition at just the right time. Okay. Again, it didn't happen, but it can happen. And because of this, I've got a friend, Jack Shirazi. He came to Crete a few years ago, and we were talking about HashMap. And he says to me, I recommend that people always use concurrent HashMap, even if they don't need it. And at first I was like, well, isn't that slower? Is that slower in the reader? No, I don't need the reader. That should be enough to cause an infinite loop. Then at first I wasn't quite sure whether what Jack was saying was correct. But then when I thought about it, he explained that basically the overhead of using a concurrent HashMap versus a normal HashMap isn't that great. It's not that much slower. And the probability of getting a race condition is actually quite high with the HashMap, because normally HashMaps are going to store data somewhere, which we're going to access from multiple threads. Now we've got an infinite loop. Right? So if you do a thread dump, you'll see that the threads are busy spinning. They're trying to do they balance the tree. It's exactly what I mentioned before. It's trying to balance it whilst it's spinning, and also trying to put. And it's happening at the same time in the infinite loop inside. And this will never end. We'll just continue running forever. If I change this to a concurrent HashMap, then again, this won't cause a problem. We'll just run without any worries. This can happen fairly easily, and it's one of those things where it's better to pay the cost, if there's a cost, of having a concurrent HashMap, but be sure that you don't have infinite loops inside your map. Because you don't know where this infinite loop is. If, for example, you serialize it to a stream, then you'll see the infinite loop. But if you're just getting individual elements, maybe you get lucky and you don't see the infinite loop. But if you hit a very specific entry, you might see the infinite loop. It might never return. And that can be a problem, right? If your server just doesn't return on certain methods, that's definitely a problem. So my recommendation is to always use the concurrent HashMap. There's actually an interface called ConcurrentMap that gives you a bunch of methods that we can use specifically for concurrent maps. And that's over here. This was added in Java 5. I see what KP is saying, that it feels like a live block. Yeah, what's happening is there's an infinite loop within the tree, right? So there's or you can get an infinite loop inside the tree. I don't know if this particular one is that, but you can get an infinite loop inside the tree where the nodes point back to themselves. And then when you use it, you hit that infinite loop and it would never return. Thanks. So the concurrent map was added in Java 1.5. Remember that map was added in Java 1.2 a long time ago. And they wanted to add methods for concurrent maps. But in those days, they didn't have the option of having default methods. This was Java 1.5. And so they added another interface which had methods specifically for concurrent maps. All the concurrent maps have something in common. They don't allow nulls. And so this is something to remember is if you have nulls coming back from, or if you try to put nulls into a map, it works with some maps, like HashMap will allow you to do that, but concurrent map does not. ConcurrentHashMap specifically doesn't do that, doesn't allow you to do that. And the problem is that there are certain methods, like for example, put if absent. And put if absent was built for ConcurrentHashMap. So if you take ConcurrentHashMap and you say put if absent, and and the element is not there, it puts it there. So for example, I'm going to say map.put if absent over here, 900, comma 1,000. Of course, that's not 900 squared, but I'm going to put in the wrong value. Now, what's going to come back here, I'm also going to change this to be not 10 million, just 100,000. It takes too long to run this code. So I'm going to print out the put if absent, the result of put if absent. Let's run that. Put if absent. And because the element is there ready, it comes back with 810,000, right? With 900 squared. But let's do the following. Let's say long L, and we're going to map the put if absent minus 900. And of course, that isn't there yet, because we haven't done negative numbers. So what we'll see is we'll see L equals null coming back. And in this case, null has a special meaning, meaning it wasn't there. It was never there. The entry is not inside. All right. So that's all fine. But now, let's imagine that we've got HashMap. So I'm going to say, is it a map? Yes. I'm going to say map equals new HashMap. Okay. I'm going to put in there map.put 900, comma, no. Okay. So what I've done is I've put in the value null for the key 900. I wouldn't be able to do that with the concurrent HashMap, but I can do that with the HashMap. So if I say put if absent 900, 1,000, if it's null, it's going to treat it as being absent. So put if absent is not the same as saying if map dot doesn't contain. Right? If contains is false. It means if get is equal to null, then put. So if I run this code, it's going to put it in. But L will be null in both cases. Oh, wait. Let's just make another map. Let's say var. Two. Place it here. Okay. This time you'll see that L would be null both times. With the difference, it's actually going to put it in. So even though it was there, you see that map 2 will have both values in there, 900 and minus 900. And this is a bit confusing because let's say, for example, I've got some code here that says if map2 dot contains key 800 or doesn't contain key 800, then I'm going to say map2 dot put 800, 16. IntelliJ will not recommend that you change it to put if absent. It won't say, hey, you could use put if absent. But if I have if map2 dot get minus 800 map2 dot put 800, so if that is equal to null, then it will recommend changing it to put if absent. And it's very subtle because there's a very slight difference. There isn't a difference with compute if absent. With concurrent HashMap, but there is a difference with HashMap. Just keep this in mind. I try not to use HashMap, but if I do, I would not put a null value into the HashMap. I would treat it as if it wasn't never having nulls. It's the classical $1 billion mistake. Probably a lot more than that. All right, TreeMap is your not thread safe map. It's sorted. ConcurrentSkipList is sorted. You can do parallel put to TreeMap. That works. I won't do that again. I've done it before. Something else which is very useful are LinkedHashMap and LinkedHashSet. For example, if I do the following, I'm going to say thread local random dot ints current dot ints, and I want to see 10,000 ints, 10,000 ints between 0 and 1,000 or 100. Okay? Between 0 and 100. And I want to make them distinct, and then I want to say to list, or rather box, and to list. And the to list here returns an immutable list. What you'll see is that the list is not going to be sorted. It's going to be ordered by whatever came first. But how does it work? How does this thing actually work? Well, what they do is they actually make a linked hash set inside the distinct. Somewhere here, box.distinct. Okay, and the stream.distinct. You look here, somewhere there they make a linked hash set. They put the elements into the linked hash set, and then they take them out in the same order which they're put in. So the linked hash set always retains the elements the order which they're put in. So for example, if I had to go another example, let's say, back to where it was. Pi. We'll make here var pi equals int stream dot stream 3.9 dot you have to figure out when it wants to import something when it doesn't. Yeah. Off. So if I say, no, I don't want to do it this way. Sorry, I want to say set of integer pi equals new linked hash set. And then I'm going to say connections dot add all pi comma 314159. So then print out the pi, you'll see 31459. Okay, so run that. You'll see 31459. Comes next to 8 or something. I've never felt the need to memorize digits of pi. My son did that once. And he went quite far. 5926535. 26535. So the elements get returned in the order in which they appear. It doesn't lose that order. If I take a normal hash set, then they get ordered pretty much by their hash code. Now, in this case, because the numbers are quite small, it's going to order them seemingly numerically. That's a bit deceptive. It's just a figment of our imagination. It's not really. What's really happening is that it's making a hash table of roughly 16. I think it's going to be over here. Yeah, size 16 probably, or 16 or 32, and then the hash code is simply the numbers. So I've put a big number in here. Let's put in, for example, 3,141 instead of 141. It's 3,141. Right? If I do that, then you'll see the 141 will be at some random place. It's at the back here. Let's do 592 653. See how that appears. They definitely don't have to be in the numerical order. Okay? So you can see it's all mixed up. But if I take a linked hash set, they'll be in the order in which they appeared in my string, or in the order in which they're added. There's also LinkedHashMap, also very useful, which can either retain elements in the insertion order or the access order. So let's make a map of, let's call it the integer cache equals new linked hash map. And then I'm going to say from 0 to 5, cache.put I, okay. Then print out the cache. You'll see it's going to be 0, 1, 2, 3, 4, 5. If I add another one, cache.put, or if I say cache.get 2, and I put the cache, it doesn't affect at all what you see. It's going to be 0, 1, 2, 3, 4, both times. However, what you can do with linked hash maps, you can actually override that. And you can make your own linked hash map. You can call, first of all, you can use a constructor that changes to use access order. Initial capacity max 16, float factor, load factor, what is that? The default? The default is going to be the default load factor, 0.75. Oh, I think it's defined inside. It's defined up here. So the default hash map would have the default load factor, which is 0.75. Yeah, that's what I thought. So we have to specify that explicitly and say true for to have an access order rather than insertion order. So if I run it like that, it's going to show me 2 at the beginning. No? At the end, so 2 at the end. That's the last one that was accessed. And then if I add another, let's add some more. Let's start this time at 5 and go to 10, go to 8, 9. Add some more elements in there and print it out again. You'll see that 2 is in the middle somewhere, and we've got then 5, 6, 7, 8 behind that. Okay. Right, now that's the access order rather than the insertion order. If you touch anything, then it moves. And what you can also do here is you can go and you can say override remove elders entry to return true if you want to remove elements. So let's say I want to have a capacity of 5, private final capacity int capacity, the maximum equals 5. I can say return size is bigger or equal to maximum. In that case, we're going to remove it. And now what you'll notice is that we're removing elements which are no longer necessary. So we only, okay, let me change it to something bigger than X. Then you should have 5 elements, and 2 should be at the beginning. 2 is now next, is the next one we're going to remove. And then 5, 6, 7, 8 are the ones which are going to be the most recently accessed. This is basically an LRU cache. It's not thread safe, so you need to be careful of that. Least recently used cache. All right, there's some other interesting caches, HashMaps or maps. There's EnumSet and EnumMap for working with enums. IdentityHashMap stores elements by identity rather than by their hash code and equals. And they use this in some places, not too many places. I think they use it. I think they used to use it. I'm not sure if they still use it. So if you look inside the JDK where this is used, find usages. I thought it used to be used in the in serialization, although they might have done it, have a different mechanism for that. So they're using it for certain mechanisms, like for example, shutdown hooks. They're using this for shutdown hooks, apparently. Code read labeler. So it's used in some places. I've used it a few times. Not very often, but occasionally. If you want to hash, but you don't want to hash by dot equals, that's when you want to use. Properties is your system get properties. System properties, it's quite useful. It used to be a hash table. In fact, it's a subclass of hash table. But nowadays, even though it is a subclass of hash table, it actually delegates all the methods to a concurrent HashMap. So if you take like an older version of Java, your properties would have been heavily contended on the writing and the taking as well, so everything was synchronized. Whereas nowadays, properties is on a concurrent HashMap, which is much faster with multiple threads reading from it. I can test that. Let's do it this way. Executor service pool equals executors with new fixed thread pool of 10, 0 to 10. For I say there's a system that get properties, and this is a properties are here, and we're going to get all the values. So let's go iterate through the key set, and we're going to say string value equals properties dot get property with the key. This actually should be an object, not a string, not an object. So the properties key set, if there's a different one we can use here, string property names. Let's take this one, string property names. This one. So iterate over that to get the properties. So I'm calling them all, and I'm going to do this with each thread. I'm going to say pool.submit. We're going to go let's make a new runnable, and we're going to iterate over that and just get the values. So do that 10,000 times. J less than 10,000. We get all the properties. We did it from 10 different threads at the same time. And here we go. So submit that. It's runnable. We're going to call pool.shutdown immediately, and we're going to see how long it takes for that to actually finish. So we're going to say, again, pool.await termination. It's going to be like 1 day. It won't take that long, I hope. We are actually almost out of time. We're already like waiting for them to mop the floor and pick the table, pick the chairs up. Patrick is like wondering about when I'm going to finish. But it's going to finish within that time. But I'm going to measure the time it takes for this to complete. That's going to be the time. So I'm going to run this in Java 21. We'll see how that performs. And it should be quite good, having multiple threads, which are all getting that information from curly braces. Curly braces there. And okay, so I don't know if that's good or bad. It looks not too bad, 692. But if you take Java 7, for example, and we're going to compile that again, 8, and we're going to run it. Yeah. And instead of saying 690 milliseconds, whatever it was, it's taking a lot longer. It's taking like 5.6 seconds. Java 21 is 600 milliseconds. And the reason for it is contention. If you go back to Java 7 and you run it, and I think this changed in Java 9, so Java 8 will still like that. So it's another reason not to be with Java 8. Java 8 will also be quite slow. Not as bad as Java 7, but not as good as Java 21. So if you want to get the properties quickly, you want to take Java 21. Back to Java 7, run it again, and I'll do a thread dump. And you'll see in the thread dump, you'll see there's going to be lots of blocked. Blocked. It's blocked. It's blocked. It's blocked. These are all blocked on the hash table. But in Java 21, they are actually delegating the calls to ConcurrentHashMap, and so the performance is much better. All right, that's your property. The other one was your WeakHashMap, which we don't use that much. It's basically a weak key, a weak reference to the key, and a strong reference to the value. So that's how that works, the WeakHashMap. I mentioned queues and Deques. There's not that much to say because these are mostly used behind the scenes. The only thing that I find useful sometimes is to use a concurrent linked queue as a thread-safe sort of list. It's not exactly a list, but it's a sort of list. Because you can't find an element at a particular index, but you can add and you can iterate over it in a thread-safe way, weakly consistent. So that's quite useful. The priority queue is as a priority heap. It's not thread safe, and it swaps out. It swaps around. It's not stable, so it swaps around multiple elements on that. The deck, we've got array deck, concurrent linked deck, and LinkedList. LinkedList you don't use. Array deck is a very nice circular array list type of thing. It's not thread safe, but if you don't need thread safety, it's quite nice to use. And then you've got different blocking decks, array blocking deck, which is super complicated. It took me 4 hours to explain. It's quite fast, but it does have contention because there's only one lock that's used for putting and for taking. The delay queue is used for the schedule executor service, so I've never used it myself outside of that. The link blocking queue is used for your fixed thread pool. The priority blocking queue you could use for a priority thread pool, although that's a bit tricky, and I know how to do it, but it requires a bit of gymnastics to get that working. And then you've got the synchronous queue, which is used for the cached thread pool. The synchronous queue is always empty, it's always full and always empty. So we call put. It always blocks until somebody else calls take. If you call take, it blocks until somebody else calls put. And then the last one is the linked transfer queue, this one over here. This one was created for the fork join pool, Java 7. So it's created for that. And then when they published, when they had the beta out, because in those days they didn't have like nowadays you've got the JEPs and you've got every 6 months a new version. So that worked quite slowly, and they presented this to the public, the fork join pool, and people came back and they said, "Oh, this performance is terrible in the fork join pool." And when Doug Lee and his colleagues looked at the code, it was always wrong. It was always like not doing it the way it's supposed to be done. And instead of trying to convince the general public that they're doing it wrong, they thought it would be easier for them to simply change the way that the fork join tool works, rather than trying to explain to the public that they did it wrong. Because people don't believe that they could have done anything wrong. So it's always the computer's fault. So they basically changed everything. They use parallel arrays now, and as a result, they don't use linked transfer queue anymore. And I don't think it's used anywhere in the JDK. Maybe there's one place, but something like linked transfer queue. Find usages. There's a Polar. The Polar uses it. I don't know when this was added. This might have been added recently, I'm not sure. But it was built for the fork join pool, but it never really found a home there. And that's really it. There's also link blocking deck if you need that. That's all your queues. Not much more to say about these. Okay. We also have facades for collections and arrays. There's collections.class and arrays.class. But usually what happens is that the methods that are very useful end up back in the various collections. So for example, the sort method. Sort was defined on collections, and they moved that to the list. Reverse was defined inside collections, and it's been moved into the list as well. And it's used into others as well. So TreeSet, for example, can be reversed, and a lot of different sets can be reversed. But there are a bunch of other methods you can use. If you look at the collections dot, you can make unmodifiable sets. Although unmodifiable doesn't get used that much anymore because we can now make. I've got to show you one more thing. This is going to be the last thing I'm going to show you, which is important. Okay. So we had our position jobs. I don't really want that position. I have my own position, but maybe I'll borrow this position. No, that won't use it. Let's take the pixel class. Okay. I'll just make my own position. Pixel. So record here, record pixel int x, comma int. Okay. Very simple pixel. And if I make I showed you this week. I showed this week. I think I showed you this where I said copy off on that. I think I showed that to you. shown it to so many people recently. I might have shown that to you. Anyway, the problem is that you can make a set, a hash set, quite easily with this pixels. So I'm going to make a set of pixels equals new hash set and naught to let's make it 200 pixels that add new pixel of I, j. Okay, and that works fairly well. It gets done quite quickly. This part here. But then what I want to do is I want to, first of all, if I want to make it immutable or unmodifiable, I can wrap it. I can say pixels equals collections, but unmodifiable set of the pixels. And now it's unmodifiable, nobody can change it. This part here is instantaneous. So that is unmod time. That's going to be like 0 milliseconds or 5 milliseconds. It's very, 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 very fast. Okay? However, if I say copy off, list or set.copy off, it is not instantaneous. Right? So if I say, I have to show you this last thing because it's important, then you'll stop. Pixels equals set.copy off pixels. So that's going to make a brand new set. This part here has got a very, very bad hashing function. So this is a copy off time. And the way it works is you get a hash code, it finds a position, and if it doesn't have, if it's occupied, it goes one step further. If that's occupied, it goes one step further. And even with 200 by 200, look at the performance. I've got a fix. I want to propose it. I haven't had a chance yet, but let me show you how well my fix works. This is Heinz's latest. It should actually be Java 22. So if you run with Heinz's latest, if it works, it should work. No, that doesn't work. So latest. So Java, EU, Java specialists, data structures. This is Java 8, 1. This was my little tweak that I did. And I might have actually, look at that. Copy time, 41 milliseconds. I think that's a little fix. As opposed to Java 21, where it takes a lot longer to more than many seconds. So this is something I want to put into the JDK, but for now, that doesn't work. So it's not in there, so you need to be very careful with objects which clash. They end up with very, very, very poor performance. So Arrays also has a bunch of classes and methods. We've come to the end. It's been an absolute pleasure. Thank you very much. Why does it prompt to have Octonaut? Because that's the name of my computer. That's my laptop. It's got 8 cores, so I just thought, well, 8 Octonaut. There you go. My daughter at the time was watching Octopus. So it was, whatever comes to mind. My new laptop is called 7 Nation because it's an ARM. It's an ARM-based computer, so it's going to be called 7 Nation. All right, so thanks very much, NJ and ST and KP and U1 and Patrick for your help. Hope you have a wonderful, wonderful weekend, rest, and see you week after next. I'm doing some more courses, so it's all coming back again. See you then. Thanks very much. Have a fantastic week.
All right. Thanks a bunch, Heinz. All right, everyone. We'll see you next week in Heinz's course. Otherwise, have a great weekend. And thanks so much, too, Heinz. See you next week as well. Take care.